Right now, as you listen to this, something extraordinary is unfolding above our heads. A traveller from the stars, designated 3I Atlas, is approaching not just our neighbourhood in space, but the threshold of our solar system itself. When astronomers first announced its discovery, it seemed like a familiar story. Another interstellar object, rare but not unheard of, drifting on a hyperbolic path that would carry it briefly through the inner regions of our system, before vanishing forever into the dark. But this time the story is not so straightforward, because this visitor has company, and the longer telescopes watch, the stranger the situation becomes. From the moment Atlas was catalogued, astronomers noticed something unusual. Other faint objects were being spotted nearby, arriving in bursts and waves that defied the expected randomness of the sky. Normally, discoveries like these are scattered across months or years, predictable in their unpredictability, the background noise of cosmic debris wandering past Earth's orbit. But here, the rhythm changed. Objects began appearing one after another as though responding to some unseen cue. A small asteroid flashing across our monitoring systems, then another only days later, then a comet brightening in the night sky at exactly the moment Atlas grew more visible. The coincidences piled up faster than the explanations, until the question could no longer be avoided. Was Atlas alone, or was it heralding something larger? The central theme that has haunted every briefing since is the tension between coincidence and cause. Science prefers randomness, probabilities, models where chance explains what looks like pattern. Paranoia whispers the opposite, that nothing this synchronized can be accidental, that something hidden is guiding these arrivals. As each new object is logged into the catalogues, the debate intensifies. Astronomers are careful with their language, calling it a clustering of detections, noting that improved survey technology increases the odds of simultaneous finds. But behind closed doors the tone shifts. What if these objects are related? What if their arrival is not just coincidence but consequence? As if Atlas were pulling a curtain back and revealing a stage crowded with performers we never expected to see. The last time the world felt this kind of unease was in 2017, when a cigar-shaped visitor, later named Oumuamua, passed silently through our skies. Its speed, its trajectory, its inexplicable acceleration led to whispers of artificial origins, debates that still haven't fully quieted. Then came 2019, and Borisov, a comet from beyond our system, blazing a more typical path but still proof that we live in a galaxy crisscrossed by wanderers. Atlas is only the third such confirmed interstellar traveller, yet it already carries a weight that the others did not. Because Atlas is not passing unnoticed. It is arriving at the same moment our skies are busier than ever, and every fresh detection makes the pattern harder to dismiss. When the first news broke, many assumed this would be another fleeting story. A curiosity for astronomers, a headline about something strange but harmless, soon forgotten by the public. But the reports didn't stop. Instead, the announcements accelerated. Minor planets sweeping closer to Earth than the Moon. Comets discovered by instruments designed for other purposes, suddenly visible to the naked eye. Each one was catalogued, explained, filed away. Yet the number of coincidences outpaced the patience of even the most disciplined researchers. As one planetary defense officer put it during an unrecorded discussion, it feels choreographed, like the universe has chosen this season to remind us just how little control we really have. It is important to remember how carefully astronomers measure the sky. Every new asteroid tracked, every comet analysed, each one folded into massive databases of orbital elements and probabilities. This is not guesswork, but precision, a machinery of numbers that has allowed humanity to feel a sense of security even in the midst of an ongoing cosmic shooting gallery. The equations tell us which objects pose no risk, which ones need more monitoring, and which ones will pass by at safe distances. But the clustering of discoveries since Atlas was spotted has bent that machinery almost to breaking, because probability says this should not be happening, not like this, not all at once. So here we are staring at the sky in a moment when rational explanation and primal fear collide. On the one hand, this could be nothing more than the side effect of better surveys. The Vera Rubin Observatory has only recently come online, sweeping vast sections of the sky with unprecedented sensitivity. It is natural that more eyes would find more things. On the other hand, the timing feels suspiciously convenient. Rubin's first light comes in June, Atlas is discovered in July, and by September the sky is a crowded theatre of objects converging as if to greet it. If you are willing to believe in coincidence, then coincidence is what you see. But if you are not, then the mind begins to wander, and once it starts wandering, it rarely stops. The sense of unease grows sharper when we consider what Atlas itself represents. This is not a member of our solar family, not a cousin from the Oort cloud or the asteroid belt. This is something from far away, another system, another star, possibly older than the Sun itself. Its orbit tells the story clearly. Hyperbolic, eccentricity greater than 1, a path that does not bend into an ellipse but stretches into infinity. This is an outsider, and outsiders often bring more than themselves. In myths and legends, a stranger at the gates is never just a stranger. It is a harbinger, a catalyst, a sign that the ordinary order is about to break. Science does not use such language, but it feels the same chill when numbers show impossibilities stacking on top of one another. What makes the story sharper is that Atlas does not threaten us directly. Its closest approach will still be hundreds of millions of kilometers away, far outside the zone of immediate danger. We will watch it, study it, and it will pass without touching us. That much is certain. The uncertainty lies in the company it seems to be keeping. The swarm of minor bodies threading their way past Earth, some within lunar distance, some glowing as comets, some vanishing after brief encounters, is the real problem. If even one of those smaller travellers had been on a collision course, the warning time would have been painfully short. Days, maybe hours. Enough to write reports, not enough to prepare defences. That is the balance of this moment. Certainty on one side, paranoia on the other. We know Atlas itself will not hit us. But the multiplying objects around it remind us that knowing one thing does not mean knowing everything. And in the vastness of space, the difference between what we know and what we don't can be the difference between a spectacular light show in the sky and the sudden rewriting of history on the ground. Stay with me on this late-night exploration as we peel away the layers of this unfolding story, from the first faint glimmers of objects that should not be clustering, to the unsettling implications of alien chemistry, to the possibility that what we are witnessing is not a fluke, but a glimpse into the deeper structure of the galaxy itself. Each step takes us further from comfort and closer to the question we cannot yet answer. Is this just a coincidence amplified by better instruments? Or are we being shown, for the first time, the reality of a galactic highway intersecting with our own world at the worst possible moment? And as we move deeper into the sequence of events, the details only grow stranger. Observers who first noticed the faint bodies appearing near Atlas's projected path began asking themselves whether gravitational interactions could possibly explain what they were seeing. Normally, a comet or asteroid passing through exerts negligible influence on other bodies. The sun and planets dominate everything. Yet the sense persisted that somehow Atlas was not alone. The story does not stop here, because the more telescopes scanned the sky, the more they found. Each new detection added to the mystery. Each fresh comet or asteroid slipping past Earth added fuel to the debate. Some scientists argued that the pattern was illusion, an artifact of human brains tuned to find order in chaos. Others countered that too many variables were aligning for it to be dismissed so easily. If this is illusion, it is one of the most convincing in history. If it is not, then we are standing at the threshold of a revelation that will change the way we understand our place in the galaxy. The first signs of something unusual rarely arrive with fanfare. They creep into the record slowly, almost quietly, and only in retrospect does the significance reveal itself. That is how the story of the multiplying objects began. A faint point of light on a telescope image, easily mistaken for noise or a known asteroid but moving just enough to warrant follow-up, then another, and another. Individually they meant little. Together they began to form a pattern that even the most disciplined astronomers could not ignore. In mid-2020, the night sky was supposed to behave like it always does, filled with predictable traffic that follows well-understood paths. The asteroids that orbit in their belts, the comets that occasionally streak inward, the countless minor objects catalogued with patient regularity. The machinery of orbital mechanics is as steady as clockwork, each orbit calculated, each pass predicted. For decades, this gave astronomers the comforting illusion that even in a universe filled with hazards, the risk could be measured, the dangers charted, and the surprises managed. But the calm of that routine was beginning to crack. The first hints came not from professional surveys, but from smaller observatories and even amateurs. People accustomed to the night sky who suddenly noticed odd movements, objects appearing in places they hadn't been before. At first, these were written off as observational errors, or simply the natural result of new sky survey equipment coming online. The Vera Rubin Observatory in Chile had only just begun operations, capable of sweeping the heavens with unprecedented depth and speed. Of course it would find more than older systems had. But the timing of those discoveries raised eyebrows. The more carefully astronomers looked at the data, the clearer it became that these weren't just routine finds scattered across random nights. They were clustering. Clustering in astronomy is not unheard of. The Kuiper belt is a cluster of icy objects beyond Neptune. The asteroid belt between Mars and Jupiter is a cluster of rocky remnants. But clustering in near-Earth space, timed so closely to the arrival of an interstellar visitor, was another matter entirely. This was the domain of coincidence, the kind of thing statistical models dismiss as improbable. Yet improbability does not mean impossibility, and improbability becomes suspicion when it repeats itself over and over. One of the earliest alerts concerned a small asteroid less than 100 meters wide, catalogued after a brief flyby at a distance closer than the Moon. Such events happen every few months and rarely make headlines. But what unsettled astronomers was that within days another object appeared, and then another, each one slipping past at distances that felt uncomfortably close. Normally these flybys are spread across weeks or months, but here they were stacked almost on top of each other. Observers began comparing notes and asking questions. Was something drawing them in? Were their orbits being perturbed by some hidden factor? Or were we simply noticing what had always been there? The key moment came when those faint detections overlapped with the trajectory of 3I Atlas. By then, the interstellar comet had already established itself as the year's astronomical story, a rare chance to study material from another star system. But when the smaller bodies seemed to echo its path, following in loose synchronization, the narrative shifted. What had been a story about a single visitor became one about a possible entourage. Of course, physics insisted that a body only a few kilometers wide could not shepherd asteroids across millions of kilometers. Its gravity was negligible compared to the planet's. Yet the timing was hard to ignore. In late nights at observatories around the world, astronomers found themselves asking questions they would never pose in published papers. What if Atlas was not just a comet? What if its arrival signaled something larger, something we hadn't accounted for? Theories sprouted quickly, most dismissed as speculative, but none easily disproven. Perhaps Atlas was fragmenting, shedding pieces too faint to be immediately obvious, leaving a trail of debris that scattered into temporary orbits. Perhaps the surge of detections was not physical, but perceptual, an illusion created by the sheer attention Atlas commanded. Or perhaps, as some dared to whisper, there was a deeper connection between the interstellar traveller and the multiplying objects now surrounding it. For the public, the story began to break in fragments. News sites carried headlines about near misses and clusters of comets, but the coverage rarely conveyed the sense of unease that dominated professional discussions. Most people are used to hearing about asteroids flying by at safe distances. Few realise how delicate the margin of safety can be. 800,000 kilometres might sound like a vast distance, but in astronomical terms it is uncomfortably close. And when such events happen in quick succession, the psychological weight multiplies. The night skies that September and October became unusually busy for amateur astronomers. Reports poured in of faint objects near Virgo, of comets sprouting tails earlier than expected, of asteroids brightening briefly as they caught the sun at favourable angles. Each new report added to the sense that something was stirring, that the background noise of the cosmos had grown louder. For the first time in years, planetary defence offices found themselves issuing multiple bulletins in rapid sequence, reassuring the public that these were harmless passes while quietly updating internal models to account for the uptick in activity. The phrase that circulated in professional circles was the Glimmers. It was not an official designation, but it captured the feeling. Small sparks of motion against the dark, faint bodies just at the edge of detectability, hinting at something bigger behind them. Some of these glimmers faded quickly, disappearing into orbits that carried them back toward the asteroid belt or out into the void. Others lingered, tracked for weeks before slipping beyond the reach of telescopes. But the cumulative effect was undeniable. The sky was not behaving normally. As more detections came in, patterns began to emerge. Several of the objects arrived along trajectories tilted at similar angles to the ecliptic, as though aligned by a common influence. Others seemed unrelated, approaching from directions that defied easy grouping, but the sheer number of them arriving in such a narrow window was statistically troubling. Even accounting for Rubin's improved detection power, the clustering exceeded expectations. By mid-autumn, some astronomers privately estimated that the probability of this being a random coincidence was less than 1%. They didn't publish those numbers. To do so would have risked sparking a panic. But the calculations were written down, shared quietly among colleagues, a reminder that science and fear are not as far apart as we like to imagine. The question that hung over every conversation was simple. Why now? What made this season different? Some pointed to gravitational resonances, subtle alignments of Jupiter and Saturn that might funnel more debris inward. Others suggested that Earth's orbit had carried us into a denser region of space dust, stirring up a temporary increase in encounters. But these explanations were unsatisfying because they failed to address the timing with Atlas. Even the most skeptical voices had to admit it was an extraordinary coincidence. In control rooms and observatories, scientists watched as Atlas itself brightened, revealing more of its alien chemistry, while at the same time logging one faint detection after another. The effect was like watching ripples spread across a pond after a stone has been thrown, except no one could agree whether the stone was Atlas or simply the improved reach of our instruments. The distinction mattered less to the public than to professionals. To most, it was enough to know that the sky was busy, perhaps busier than it had ever been in living memory. And so the first glimmers in the dark became something larger than themselves. They were no longer just minor objects catalogued and forgotten. They were omens, signs of a sky unsettled, shadows hinting at a drama still unfolding. As Atlas moved closer, the glimmers multiplied, and each one carried the same question. Were they random wanderers passing through, or were they pieces of a pattern we had only just begun to perceive? The real shock came not from a single object, but from the way their numbers began to climb. One detection might be dismissed, two might be coincidence, three could be bad luck or timing. But when the tally grew into dozens within the space of weeks, even the most cautious voices had to admit something was happening. The multiplication was undeniable. In ordinary years, the Global Asteroid and Comet Detection Network announces new discoveries at a steady, predictable pace. Minor bodies sweep past Earth at regular intervals, some large enough to earn headlines, most too small to bother the public with. The patterns are well understood, and for the most part astronomers take comfort in how routine it all feels. That comfort evaporated in the autumn of 2025. Instead of one or two close approaches a month, there were clusters of them, stacked days apart, sometimes hours apart, each arrival shadowing the last as if some invisible clock was striking in the background. It started with objects barely 100 meters across, the kind that can still inflict regional devastation if they were ever to hit Earth. Their flybys were close, within lunar distance, often far closer than the orbits of our satellites. Then came larger bodies, hundreds of meters wide, sweeping past at what the headlines called safe distances, though safe meant only that they did not collide. In practical terms, they were closer than anyone was comfortable admitting. The statistics piled up until the story could no longer be contained to dry orbital charts. Something about the timing forced its way into the conversation. The multiplication effect was not just about numbers, it was about perception. Each new discovery seemed to echo the last, like a rhythm building momentum. Scientists accustomed to dismissing human pattern recognition as a weakness found themselves reluctant to say the word coincidence. The flood of new detections was too fast, too neatly stacked, and too persistent. The usual explanations that improved surveys naturally uncover more objects, that the Vera Rubin Observatory was rewriting the statistics, felt thin when laid against the raw scale of what was being recorded. Consider what was unfolding in real time. Every day brought fresh orbital diagrams, fresh press releases, fresh alerts to planetary defense offices. Comets materialized in the data streams of spacecraft designed to study the solar wind, their hydrogen signatures flaring against the background. Near-Earth asteroids passed within margins so tight they triggered temporary listings on risk registers before follow-up observations removed them. One or two of these events would have been enough to energize the community for weeks. Now they were coming so fast that scientists barely had time to finish one report before beginning the next. The numbers painted the picture most clearly. By late September, detections of sub-lunar distance flybys had already doubled the average for an entire year. By October, the total had tripled, and alongside them came comets bright enough to be seen without telescopes, some fragmenting, some flaring with sudden outbursts, all adding to the sense of acceleration. It was as if the sky had decided to stage a performance, with Atlas as the headline act and a supporting cast of minor bodies filling every available scene. For the professionals tracking these events, the workload was staggering. Teams that normally rotated through routine observation schedules found themselves working round the clock, coordinating across continents to verify orbits and rule out risks. The International Asteroid Warning Network became a hive of urgent chatter, messages bouncing between observatories as each new detection was cross-checked. The burden was not just technical but psychological. Scientists who had trained themselves to avoid alarm found themselves quietly unsettled, aware that the systems designed to reassure the public were being tested harder than ever before. And yet, amid the multiplication, there was still no evidence of direct threat. Each object, when tracked carefully, passed at distances that posed no immediate danger. The multiplication effect, then, was not about catastrophe, but about tension. The sense that the universe was playing with the odds, reminding us how thin the line is between safety and disaster. Every flyby reinforced the reality that if even one of those objects had been nudged slightly differently, the outcome could have been very different. The public began to take notice as headlines repeated the phrase, "another close approach." At first the tone was casual, a curiosity piece about how often Earth is visited by cosmic debris. But as the days stacked into weeks, the repetition bred unease. Readers who might ignore a single story began to wonder why the same warning kept appearing, why the names and designations changed but the theme remained constant. For the first time in decades, the idea of multiple incoming objects ceased to be a plotline from disaster films and began to feel like an actual possibility. Behind the scenes, debates sharpened. Was this an artifact of detection bias, nothing more than our instruments finally catching what had always been there? Or was there a deeper mechanism at work, some hidden dynamic funneling objects inward at exactly the moment Atlas approached? Statistical models were rewritten, simulations run, scenarios tested. Some results suggested that gravitational resonances could, in theory, channel small bodies into Earth-crossing paths in waves. Others argued that no known mechanism could explain the sheer simultaneity of the detections. The multiplication was real. The cause was not. The timing was impossible to ignore. Atlas, an interstellar object carrying alien chemistry, was approaching perihelion just as the swarm intensified. The temptation to link the two was overwhelming. Even scientists who publicly dismissed the idea as fanciful admitted privately that the correlation felt uncanny. To suggest causation was unprofessional, yet to deny the strangeness felt dishonest. Somewhere between those extremes lay the truth, but it remained just out of reach. The multiplication effect reshaped the way astronomers thought about their work. Instead of isolated encounters, they began to consider the possibility of waves, surges of activity that arrive not randomly but in bursts. If true, that would imply the solar system is not as steady as once believed but vulnerable to episodes of heightened traffic. These episodes might be rare, separated by decades or centuries, but their impact on planetary defense planning would be profound. Systems built to handle one threat at a time might be inadequate for a dozen arriving simultaneously. As the weeks wore on, the multiplication showed no sign of slowing. Comets continued to brighten, asteroids continued to skim past, and Atlas itself glowed brighter with each observation. The sense of escalation grew heavier, not because disaster was imminent, but because it suddenly seemed more plausible. If this was what the sky looked like with no impacts, what would it look like if even one object strayed off course? The imagination needed little prompting to supply the answer, and so the multiplication effect became both a technical reality and a cultural phenomenon. For the scientific community, it was a challenge to understanding, a problem that demanded new models and deeper explanations. For the public, it was a drumbeat of headlines that hinted at something larger stirring in the cosmos. And for those who watched the data streams late into the night, it was a reminder that certainty in astronomy is fragile, that patterns emerge where none should exist, and that sometimes the universe refuses to play by the rules we expect. The story was no longer about a single interstellar visitor. It was about the flood of company it seemed to attract, the multiplying objects that turned ordinary nights into a blur of detections and near misses. Whether coincidence, consequence, or something more, the effect was real, and it was only the beginning of what the sky was about to reveal. The human mind is built to wrestle with chance. From the roll of dice to the patterns of weather, we instinctively weigh odds and search for meaning in randomness. In the world of astronomy, probability is not just a curiosity but a tool, the backbone of how risks are measured and predictions are made. Every asteroid orbit carries with it a percentage, a likelihood of future impact, a chance of safe passage. These probabilities are calculated with such precision that entire defense strategies are built around them. Yet what unfolded with the arrival of Atlas and its multiplying companions began to stretch those probabilities until they threatened to break. At first, the calculations seemed routine. Each new object was assigned its risk corridor, each probability plotted and updated as more observations came in. That is the rhythm astronomers know well. Detection, tracking, refinement, reassurance. But as the swarm thickened, the models grew increasingly uncomfortable. The sheer clustering of objects was the problem. The odds of so many bodies arriving so close in such a narrow window should have been vanishingly small. Probability said this could not be happening, yet the sky insisted otherwise. The paradox emerged clearly in late September, when analysts began running simulations of near-Earth object arrivals over timescales of decades. These models generate millions of hypothetical encounters, assigning them probabilities based on known orbital distributions. In nearly all runs, close approaches cluster loosely, spread across months or years. Very rarely do more than 2 or 3 fall within the same week. But the reality unfolding above Earth showed half a dozen in the span of days, with more stacking behind them. The simulations could not reproduce it. That was the first sign that something deeper was at play. Astronomers are cautious when faced with anomalies. The first instinct is always to blame the instruments. Perhaps the new survey telescopes were misreporting detections. Perhaps the algorithms were oversensitizing to faint trails. But checks and cross-checks confirm the discoveries. Independent observatories verified the objects, and radar confirmed the orbits of the larger ones. The detections were real, which left only 2 explanations. Either the models were wrong, or something extraordinary had happened. The models are built on centuries of accumulated observation. They assume that near-Earth objects arrive in ways that reflect gravitational perturbations, resonances, and the slow diffusion of bodies from the asteroid belt and beyond. These assumptions had always matched reality, until now. The paradox of probability was that the sky was presenting a scenario with odds so low that they bordered on impossible, yet impossible events were materializing one after another. This did not go unnoticed. At professional conferences and private discussions, the unease was clear. One statistician compared the situation to flipping a coin 100 times and seeing it land on heads for 80 of them. Not impossible, strictly speaking, but so improbable that to see it happen demands you question whether the coin is fair. That was how the clustering felt. Maybe the sky was still random, maybe the probabilities still held, but the outcome suggested something more than chance was guiding events. The paradox forced scientists into uncomfortable territory. They began asking whether something unseen was shaping the arrivals. Could Jupiter's gravitational field have aligned in such a way to funnel debris inward at just this moment? Could solar activity have perturbed cometary orbits more dramatically than expected? The answers were unsatisfying. While resonances and perturbations can shape populations over long timescales, they do not explain sudden bursts of arrivals compressed into weeks. Nothing in the known dynamics accounted for the intensity of this moment. The paradox of probability cut deeper because it threatened more than just models. It challenged the assumption that the cosmos is a place where chance governs fairly. If probability says one thing and reality shows another, the entire foundation of risk assessment falters. How can planetary defense operate if the odds themselves bend under circumstances we do not understand? It is one thing to prepare for random impacts scattered across centuries. It is another to face a scenario where randomness seems to fold into patterns. The public rarely hears about the mathematics behind impact risk, but those inside the field live by it. Tools like the Torino scale or the Palermo scale translate probabilities into categories that governments and media can digest. A 1 in 10,000 chance of impact might sound alarming, but in practice it often falls into low categories, dismissed after a few days of refinement. This system works only if probabilities behave as expected. But during the Atlas multiplication, probabilities lost their meaning. When the unlikely becomes routine, how do you assign risk? When the coin keeps landing on heads, how do you reassure anyone that tails will come next? As the paradox deepened, comparisons to past anomalies resurfaced. Oumuamua in 2017 had confounded expectations with its unexplained acceleration. Borisov in 2019 had behaved more like a normal comet, but still carried the strangeness of interstellar origin. Atlas was already set apart by its alien chemistry, but now it carried the added weight of improbability. It was not just one odd object. It seemed to be part of a sequence that probability insisted should not exist. That made it more unsettling than either of its predecessors. The human element in this cannot be ignored. Astronomers are trained to be skeptical, to resist the pull of conspiracy or speculation. Yet they are also human, and humans are wired to recognize patterns. The paradox of probability played directly into that wiring. The more they told themselves it was random, the more the clustering looked like a signal. Even those who laughed off the idea of orchestration admitted privately that the timing gnawed at them. If this was all coincidence, It was one of the most remarkable in living memory. The paradox spread beyond the scientific community. Media outlets began to run stories that hinted at hidden meanings, at cosmic choreography. Social media amplified every detection into part of a larger narrative, weaving them together as though they were chapters in a story. The idea of randomness failed to satisfy curiosity. People wanted explanations, and in the absence of certainty, imagination filled the gaps. Some claimed the objects were fragments of Atlas itself, others suggested they were scouts or warnings, still others saw them as evidence of hidden gravitational forces. Probability became irrelevant once the story took root in the public mind. For planetary defense planners, the paradox had practical consequences. Resources are allocated based on risk assessments. If probabilities suggest only a few objects per year warrant close monitoring, then systems are built for that workload. But when dozens arrive at once, even if none are on collision courses, the system strains under the pressure. The paradox revealed a vulnerability, that our defences assume randomness will distribute threats evenly. If reality delivers them in bursts, the defences may be overwhelmed, not by impacts but by the sheer volume of close approaches. In the months that followed, the paradox became a test case. Scientists began revising their models, experimenting with frameworks that allowed for clustering. Some looked to galactic dynamics, wondering if interstellar tides could occasionally stir local populations into waves. Others examined the possibility of unseen populations, reservoirs of small bodies that spill inward under certain alignments. None of these explanations satisfied everyone. The paradox remained unresolved, a lingering question mark over an already unsettling season. And all the while, Atlas continued its journey, brightening, shedding gas, revealing chemistry that made it even stranger. Its presence in the background of the multiplication was impossible to ignore. Even those who rejected the idea of causation admitted the irony. The paradox of probability was playing out precisely as an interstellar visitor passed through, as though the universe wanted to ensure the event would not be forgotten. The deeper question was whether this was a one-time anomaly or the beginning of a new pattern. If clustering could happen once, it could happen again. If improbabilities could collapse into reality, then probabilities themselves had to be re-examined. The paradox did not just describe the events of 2025. It pointed forward, toward a future where our understanding of chance in the cosmos might need rewriting. And so, what began as a statistical puzzle became something larger. It became a reminder that even in a universe governed by laws of physics, uncertainty never disappears. That even in a world of probabilities, the improbable sometimes wins, and that when it does, the line between coincidence and consequence blurs in ways that leave us unsettled, watching the sky for the next impossible event that probability says should not exist. The detections that filled the autumn skies were more than just statistical oddities. As the multiplication continued, astronomers began to notice that many of these bodies did not follow the expected patterns of approach. Instead of arriving from the broad swathes of sky where most near-Earth objects originate, a surprising number seemed to appear suddenly, as though slipping in through hidden doorways. These strange approach vectors became the subject of intense scrutiny. The term that started to circulate quietly, almost hesitantly at first, was corridors. Invisible paths leading inward, narrow windows through which bodies seemed to emerge without warning. Ordinarily, the detection of an asteroid or comet follows a predictable timeline. Survey telescopes pick up a faint moving point of light. Observations over subsequent nights refine its orbit. Gradually, its origin becomes clear. Most near-Earth asteroids trace their lineage back to the main belt between Mars and Jupiter. Some comets hail from the Kuiper belt or the distant Oort cloud. Their orbits are shaped by resonances with giant planets, nudged over millions of years into eventual paths that cross Earth's. This machinery of celestial mechanics is slow, ponderous, and well mapped. But what began to trouble astronomers during Atlas's approach was how many new objects seemed to bypass this machinery altogether. Some appeared almost without warning, detected only days before close approach. Others entered from high inclinations, descending steeply toward the inner solar system as though on rails laid down by some unseen force. Their orbits did not trace the gradual inward spiral that models predict. Instead, they suggested sudden arrivals from regions of the sky that had been all but empty in survey records. For scientists who spend their careers studying orbital dynamics, these patterns carried an unsettling implication. It was as if the solar system contained entry points we had not noticed before, quiet corridors that allowed bodies to slip inside with minimal detection until they were already upon us. The concept of unseen corridors is not entirely alien to celestial mechanics. Gravitational interactions create regions of stability and instability, highways and exit ramps along which objects can move with surprising efficiency. The Lagrange points near planets are examples, zones, where gravity balances just enough to trap or guide smaller bodies. The so-called invariant manifolds, mathematical structures that govern the flow of orbits, are another, invisible skeleton underlying the solar system's motion. Spacecraft engineers sometimes exploit these features to save fuel, riding natural gravitational pathways from one orbit to another. But to see so many natural bodies apparently exploiting similar routes, converging at the same time, was unexpected in the extreme. Astronomers began plotting these new arrivals backward, projecting their orbits into the past to see where they might have originated. What they found was frustratingly inconclusive. Many of the paths faded into uncertainty beyond a few decades, their origins obscured by small perturbations that compounded over time. A few seemed to trace back toward the outer solar system, but without the long lead-up expected from traditional reservoirs. They had simply appeared, as though dropped into the system fully formed. Others defied even that. Their orbits pointed outward into interstellar space, but not in the smooth, hyperbolic curves expected of visitors like Oumuamua or Borisov. Instead, they suggested trajectories that skimmed close to the solar system before diving inward, as though guided deliberately toward the inner regions. The suspicion that something larger was at play grew stronger with each analysis. Some scientists proposed that we had underestimated the number of bodies lurking just beyond Jupiter, hidden in resonant orbits that only occasionally allow them to leak inward. Others speculated that dense streams of debris might thread the galaxy, invisible until they intersect with a system like ours, releasing clusters of objects all at once. But these explanations struggle to account for the timing. Why now in the same season that Atlas appeared? Why so many, arriving in such similar ways? To the public, these were just more near-Earth objects, more comets with unfamiliar names. But behind the scenes, the language became darker. Some compared the corridors to ambush points, invisible passages through which objects could approach undetected. The vulnerability was obvious. If a rock hundreds of meters wide could appear on a trajectory revealed only days before impact, then even the best planetary defense strategies offered little security. The corridors were blind spots, and blind spots were dangerous. The notion of unseen corridors resonated with more than just astronomers. In the late-night hours when speculation grows bolder, parallels were drawn to the idea of wormholes in science fiction, shortcuts through space-time that allow travel across impossible distances. No one suggested literal wormholes, of course, but the metaphor was tempting. Just as wormholes bypass ordinary space, these orbital corridors seem to bypass ordinary expectations. They made the solar system feel less like a closed system and more like a porous one, connected to unseen reservoirs of debris beyond our ability to map. The data piled higher as autumn turned toward winter. Radar stations pinged incoming asteroids, revealing details of their shape and spin. Some were oddly elongated, reminiscent of Oumuamua. Others were binary pairs, tumbling as they passed, Their variety was striking, but their suddenness was more so. The corridors seemed to deliver a mixture, as though drawing from multiple sources. For planetary defense officers, this was both fascinating and terrifying. Fascinating because it hinted at a structure of orbital dynamics more complex than previously imagined. Terrifying because it meant prediction was harder than ever. The corridors also raised questions about the limits of our surveys. The Rubin Observatory and others like it had dramatically increased our reach, but the objects slipping through suggested blind spots still remained. Some approached from regions near the Sun, where glare makes detection nearly impossible. Others came from high inclinations, sweeping down from above or below the plane of the solar system, where fewer telescopes scan. It was clear that even with our best instruments, we were missing more than we were catching. The corridors were not just physical, they were observational, gaps in our vigilance that the cosmos exploited mercilessly. The timing with Atlas continued to gnaw at the scientific community. Its path through the solar system was itself unusual, steeply inclined and hyperbolic, the unmistakable mark of an interstellar origin. And now, as it drew closer, these corridors seemed to open wider, spilling more objects into Earth's vicinity. Some began to wonder if Atlas had disturbed regions we could not yet see, gravitationally or otherwise shaking loose hidden populations that now cascaded inward. Others resisted such speculation, reminding colleagues that correlation does not mean causation, yet the coincidence remained. The corridors seemed to flare into activity at precisely the moment an interstellar visitor crossed the system's threshold. The implications of these corridors were sobering. For decades, humanity has operated under the assumption that planetary defense is a solvable problem. With enough telescopes, enough tracking, enough technology, we can predict and prevent impacts. But the corridors suggested otherwise. They hinted at a solar system where unpredictability is baked in, where objects can arrive too suddenly to allow meaningful defense. They reminded us that we live in a universe far larger than our models, and that our sense of security may be built on foundations more fragile than we admit. As more objects emerged from these hidden paths, the conversation shifted from curiosity to urgency. The corridors were no longer just theoretical, they were active, delivering one object after another, forcing astronomers to scramble in real time. And as the weeks passed, the question grew harder to avoid. Were we witnessing a temporary anomaly, or had we uncovered a permanent feature of our cosmic neighbourhood? If permanent, then the future held not just the possibility, but the certainty of more waves, more multiplications, more sudden arrivals from unseen corridors we barely understand. The story pressed onward as Atlas itself drew closer, glowing brighter, its chemistry revealing secrets of a distant birthplace. But its presence was no longer the only mystery. Around it, within it, and perhaps because of it, the solar system's hidden corridors had opened, and what passed through them was rewriting the way we think about cosmic chance and cosmic threat. Every time a new anomaly is discovered in the sky, the mind turns back to what came before. Patterns aren't just drawn forward, they echo backward, reshaping how past events are remembered. The multiplying objects around Atlas forced astronomers and the public alike to revisit the stories of earlier visitors, to ask whether those events were truly isolated, or whether they were the first notes of a longer song that only now is reaching its crescendo. The first and most famous of these echoes was Oumuamua. In 2017, a telescope in Hawaii detected an object moving so fast and on such a steep trajectory that it could only have come from beyond our solar system. Its shape appeared elongated, unlike anything previously observed. Its brightness fluctuated in ways that defied easy explanation. Then came the strangest part, the non-gravitational acceleration, a subtle but undeniable push that could not be accounted for by the pull of planets or the sun. For years the debate has raged about what Oumuamua was, a fragment of a shattered world, a hydrogen iceberg sublimating in unfamiliar ways. Or something even more radical, an artifact from an alien civilization? Officially, the mystery remains unresolved. Unofficially, it lingers as a ghost, a reminder that not everything fits neatly into the categories we prefer. Then came Borisov in 2019, the second confirmed interstellar object. Where Oumuamua had been strange and elusive, Borisov looked more familiar. A comet, complete with a tail and coma, behaving much like the comets born within our own system. Yet even this familiarity carried weight. It was confirmation that interstellar wanderers are not once-in-a-lifetime anomalies, but part of a larger reality. Our solar system is not isolated. It is porous, constantly intersected by debris from distant stars. The galaxy, it seemed, is filled with such objects, and we had only just begun to notice them. Atlas, arriving in 2025, became the third. But unlike Oumuamua and Borisov, Atlas did not travel alone. Its echo was not in a single trajectory or a single mystery, but in the multiplication of companions surrounding it. That is what made the echoes of past visitors feel newly ominous. If Oumuamua was a scout and Borisov a confirmation, then Atlas felt like escalation. And in that escalation, the mind cannot help but wonder if these events are connected across time. Some astronomers, looking back with fresh eyes, began to question whether Oumuamua and Borisov had been as isolated as they seemed. Could there have been smaller bodies overlooked in their wake? Did we miss subtle multiplications because our instruments were less sensitive at the time? These questions gained weight as Rubin and other observatories revealed just how much can hide in the darkness. If the sky is filled with unseen corridors and clusters, then perhaps Oumuamua and Borisov were not lone visitors at all. Perhaps they too had been part of larger streams, only partially glimpsed by our older, weaker tools. The echoes extended even further back in history. Ancient comets recorded by Chinese, Arabic, and European astronomers were revisited in light of the new discoveries. Were any of them interstellar? Could unusual trajectories dismissed at the time as errors actually have been early signs of outsiders? Historians of astronomy began scouring records for anomalies, for mentions of comets that appeared suddenly from steep inclinations or vanished too quickly to be explained. In the multiplication around Atlas, the past was being rewritten. What once looked like isolated curiosities now resembled fragments of a larger pattern. For the public, the echo stirred imagination as much as science. Oumuamua had already planted the seed of speculation about alien technology. Borisov reinforced the idea that our system is constantly crossed by outsiders. Now Atlas, with its strange chemistry and multiplying entourage, gave that speculation a new urgency. The question was no longer whether interstellar objects exist, they clearly do, but whether their arrivals are random or part of something coordinated. The echoes suggested the latter. They suggested that what we thought were isolated events might instead be stepping stones in a larger story we are only beginning to glimpse. Scientists resisted such leaps. Correlation, they reminded everyone, does not equal causation. Oumuamua, Borisov and Atlas may simply represent the normal distribution of interstellar wanderers, made visible now only because our tools have finally reached sufficient sensitivity. Yet, even as they said this, many admitted privately that the coincidences were hard to ignore. 3 interstellar detections in less than a decade after centuries of none, coinciding with a sudden surge of near-Earth activity. The probability seemed low. The paradox lingered. The echoes also touched on culture. Oumuamua entered public imagination as a mysterious visitor, the subject of books and countless articles. Borisov passed with less drama, overshadowed by the familiarity of its cometary appearance. Atlas, however, reignited the fascination. Its glow, its chemistry, its apparent entourage, all made it a focus of curiosity and anxiety. And in that curiosity, people revisited the earlier stories, connecting dots that scientists had carefully kept separate. To the public, the echoes were obvious. To the professionals, they were a troubling reminder of how fragile the line is between data and narrative. In closed-door meetings, planetary defense officers asked difficult questions. If Oumuamua had been accompanied by smaller fragments we missed, what would that have meant for Earth? If Borisov's passage had coincided with a hidden cluster, would we have been ready? And if Atlas's multiplication was not a fluke, but a feature of interstellar encounters, what did that imply for the future? Each question carried the same implication. Our sense of security may rest on a false assumption of isolation. As Atlas brightened in the night sky, the echoes grew louder. Observers could not look at it without thinking of Oumuamua's strange acceleration, without recalling Borisov's alien dust, without imagining what future objects might bring. The multiplication effect made these memories sharper, binding them together into something that felt like progression. The past was no longer behind us. It was present in every new detection, every fresh orbital plot, every unexpected comet brightening against the stars. And so, the echoes of past visitors haunted the season. They reminded us that Atlas was not unique, but part of a sequence, perhaps even part of a structure we cannot yet see. They reminded us that improbability does not mean impossibility, that what once seemed extraordinary can become routine, and that every visitor leaves behind not just data, but questions. Questions that multiply just as the objects themselves multiply, until the sky feels less like a place of random wanderers and more like a stage upon which a longer story is unfolding. The first thing that caught attention about Atlas, beyond its orbit and its uncanny timing, was its colour. In early images taken from ground-based observatories, it already appeared faintly green, a glow that deepened as it brightened on its inward path. For astronomers, colour is never cosmetic. It is chemistry, a fingerprint in light, a story written in spectral lines. And what Atlas revealed was as strange as it was unsettling. Most comets acquire a greenish tint when they near the sun, the result of diatomic carbon fluorescing under ultraviolet radiation. This is not unusual in itself. Many comets show some degree of green, particularly as they develop tails. But Atlas displayed it early, long before its distance to the sun should have produced such intensity. The glow was stronger than models predicted, brighter in certain bands, and accompanied by chemical ratios that defied easy explanation. Observers began referring to it informally as the green signal, shorthand for the mystery wrapped up in its spectra. The phrase spread quickly, because the data refused to settle into normal patterns. Spectrographs showed strong carbon bands, but also unexpected suppression of water lines, as though the comet carried less ice than expected. Other readings hinted at unusual metallic traces, nickel and cobalt in concentrations that seemed off-kilter compared to comets born in our own system. Every observation layered strangeness on top of strangeness, and all the while the glow continued, a steady beacon in the darkness. The green signal became a subject of fascination, not just for professionals, but for anyone who followed the news. To the public, the glow looked eerie, like a coded message from elsewhere. To scientists, it was no less unsettling, because it implied origins in conditions unlike anything we know. Comets formed in the Kuiper Belt or Oort cloud carry signatures shaped by the early solar system. Their chemistry is a record of the disk of gas and dust that birthed the planets. But Atlas came from somewhere else entirely, a star system light years away, a place with its own history, its own recipes of chemistry. The green signal was its biography written in light, and it was unlike any we had seen before. The intensity of the colour fueled speculation. Was this simply a comet rich in diatomic carbon, preserved for eons in the cold of interstellar space until now? Or was it something stranger, a body with an entirely different chemical architecture? Some wondered if the depletion of water meant Atlas was older than expected, formed in an environment where ices were rare or stripped away. Others suggested it might be a fragment of a larger body, torn from a world with processes we cannot yet imagine. Each explanation opened new questions, and none silenced the unease. What made the green signal especially compelling was the way it seemed to fit the timing of the multiplication. As more near-Earth objects appeared in the weeks around Atlas's approach, the comet itself glowed brighter, as though its strange chemistry were tied to the unfolding story. Rationally, the two phenomena were separate. Atlas carried its chemistry from birth, while the multiplying objects came from other sources. But perception has power. To those watching, it felt as if the glow itself were a signal, a beacon announcing not just Atlas, but the company it seemed to keep. In the background, historical echoes gave the glow even more weight. Ancient records describe green comets as omens, eerie portents of disaster. The sight of an emerald streak across the night sky once sent kingdoms into panic, armies into retreat, and prophets into frenzy. We now understand the chemistry, but the primal reaction remains. A glowing green body is unsettling on a visceral level, a reminder that the cosmos does not always present itself in comforting colours. The green signal of Atlas reawakened that unease, blending science with ancient superstition in ways no one could fully separate. As more telescopes gathered data, the oddities deepened. Some readings suggested Atlas was unusually porous, its surface shedding gas in ways that produced erratic outbursts. Others hinted at layers of different materials, as though the object were built from fragments of multiple sources. One team argued that the chemistry pointed to a system with a higher abundance of heavy elements than our own, a star that lived and died long before the Sun, scattering enriched debris across interstellar space. If true, Atlas carried within it the memory of ancient stellar death, a shard of a world that existed before Earth was born. The green glow was not just strange chemistry, it was history, compressed into light. But to many, the signal felt like something more. The way it brightened, the way it stood apart from background stars, the way its timing aligned with the swarm, it seemed almost deliberate. Of course, astronomers resisted such language, wary of speculation that might veer into sensationalism. Yet privately, some admitted the coincidence was haunting. If the green signal were a message, what would it be saying? That outsiders exist? That we are not alone in the galaxy? Or simply that the cosmos is filled with chemistries stranger than we imagined, and Atlas happened to carry one of them? The public imagination filled the gaps. Online discussions exploded with theories about coded signals, alien biochemistry, or even deliberate communication. Artists painted visions of emerald-lit skies. Storytellers wove tales of messengers from other worlds. The science remained careful, but the narrative outpaced it, feeding on the unease that always accompanies unexplained phenomena. The green signal was no longer just chemistry, it was a cultural event, a symbol of something larger pressing in on human awareness. Meanwhile, astronomers pushed forward with more data. Space-based telescopes analysed Atlas across the spectrum, from ultraviolet to infrared. Each band told a slightly different story, reinforcing the strangeness. The ratios of gases were off. The isotopic fingerprints hinted at environments unlike any in our neighbourhood. The more detail emerged, the less Atlas resembled any comet we had seen before. It was not simply unusual, it was alien in the truest sense of the word. Born elsewhere, shaped elsewhere, and carrying the unmistakable evidence of that elsewhere within its glow. The green signal also underscored the limits of our understanding. We have studied thousands of comets within our system, but all of them are products of the same family, cousins of the same solar parent. Atlas shattered that familiarity. Its chemistry was a reminder that the galaxy is vast, that worlds are forged under conditions radically different from ours, and that visitors from those worlds will not conform to our expectations. The signal was not a message in the intentional sense, but it was a message nonetheless. It said, "You are not the only story. There are others, and they will arrive whether you are ready or not." As Atlas drew closer to the inner solar system, the green signal intensified. Photographs captured its eerie glow, spreading across the sky like a bruise of light. Amateur astronomers joined professionals in recording its progress, their images filling the internet with shades of green unlike anything seen in decades. For those who watched night after night, it felt less like observing a comet and more like witnessing an unfolding drama, a cosmic theatre in which chemistry played the role of language. The multiplication of objects continued alongside it, feeding the sense that the glow was part of something orchestrated. Every new asteroid detection, every unexpected comet, every sudden outburst seemed framed by the backdrop of the green signal. Rational explanations continued to circulate, but the unease grew. It was too much, too fast, too coincidental. The glow became a symbol of that unease, the visible face of a mystery that stretched far beyond a single comet. In the end, the green signal forced a reckoning. It reminded us that interstellar visitors are not just curiosities but ambassadors of strangeness. They carry chemistries, histories, and mysteries that unsettle our assumptions. They blur the line between coincidence and consequence, between randomness and signal. Atlas, glowing green against the stars, was not just another comet. It was a reminder that the universe is deeper, stranger, and more connected than we have yet imagined. And as the signal brightened, the multiplying objects continued their silent approach, as though answering a call that only they could hear. What unsettled everyone most in the weeks after the green glow of Atlas became undeniable was not simply the comet itself, but the way the sky seemed to grow crowded around it. One by one, then two by two, then in bursts that felt unnatural, the detections kept coming. Objects slipping in from odd angles, asteroids brushing past within days of one another, faint comets brightening just enough to be seen and then vanishing again. The sense of multiplication that had been building for months now gave way to something more tangible. It felt like a gathering, as if the solar system itself had suddenly become host to a swarm. The word slipped into use quietly, at first in private exchanges between astronomers comparing data streams late at night. A swarm of near-Earth objects, a swarm of detections, a swarm of visitors crowding the orbital charts. Before long, it was impossible to avoid. The pattern of arrivals had gone beyond statistics, beyond coincidence, into something that demanded a name. The swarm was beginning, and no one could explain why. From the ground, the effect was dramatic. Observatories reported multiple discoveries per week, sometimes per night. Radar stations pinged objects barely discovered days before, their echoes confirming shapes and spins that were anything but ordinary. Some appeared as elongated shards, tumbling through space with chaotic rotations. Others were compact, binary pairs locked together by fragile gravitational bonds. A few displayed faint comae, halos of gas that suggested they were active comets rather than inert rocks. The diversity was startling, but what mattered more was the density. Never before had so many objects been logged in so short a span of time. It was not simply a matter of raw numbers. The timing was unnerving. Many of these bodies crossed near Earth within days of one another, their paths crowding orbital plots that usually feel sparse and orderly. Instead of clean lines sweeping gracefully past our planet, the charts became tangled webs. Arcs overlapping arcs, trajectories nearly intersecting before diverging again. For scientists accustomed to the elegance of celestial mechanics, the sudden messiness carried an almost visceral discomfort. The sky no longer looked like clockwork, it looked like traffic. Theories sprang up quickly, each one tested and discarded almost as fast. Some argued that the swarm was nothing more than the inevitable result of better technology, Rubin's wide-field sweeps catching what had always been there. But that explanation faltered under scrutiny. Even accounting for improved sensitivity, the spike in detections exceeded expectations. Others proposed that gravitational resonances, perhaps involving Jupiter or Saturn, were funneling objects inward. Yet resonances act slowly, over decades or centuries, not in sudden bursts compressed into weeks. The mismatch was glaring. Another suggestion was that Atlas itself had triggered the swarm, not through gravity, its mass was far too small, but through some subtler mechanism. Perhaps it had disturbed a cloud of debris as it passed, shaking loose fragments that had been lurking unseen. Or perhaps its interstellar trajectory intersected with a hidden stream of material drifting through the galaxy, a stream now spilling into the solar system. None of these ideas were comfortable, but they reflected the growing sense that something larger was unfolding. For planetary defense officials, the swarm was a nightmare scenario come to life. Their systems were designed to handle a handful of threats at a time, not dozens arriving in rapid succession. Even though most posed no immediate risk of impact, the workload of tracking them all, calculating their probabilities, and reassuring the public strained resources to the breaking point. Every new detection triggered a cascade of alerts, updates, and follow-up observations. The machinery of reassurance was running hot, and everyone knew that if even one object showed signs of a potential collision, the entire system could tip into crisis. The public, for its part, absorbed the story in fragments. Headlines spoke of another close approach, yet another asteroid, a surge of comets. At first, the repetition dulled the impact, but as the weeks passed, unease crept in. People began to notice the rhythm. They asked why so many objects were appearing all at once, why news about the sky had become a drumbeat instead of an occasional novelty. Social media amplified the anxiety, weaving every detection into a narrative of cosmic threat. The word swarm leapt from private conversations into public discourse, and once it did, there was no taking it back. Images from observatories only heightened the mood. Time-lapse photographs showed streak after streak crossing the same patch of sky, faint lines betraying the passage of multiple bodies in a single night. Charts that once displayed orderly ellipses now resembled spiderwebs, dense with overlapping arcs. Amateur astronomers contributed their own observations, confirming what the professionals already knew. The sky had grown crowded, and the crowding was accelerating. The swarm was not uniform. Some objects skimmed close to Earth, inside the orbit of the Moon. Others passed at millions of kilometers, far enough to be harmless but close enough to be noticed. A few, more worrying still, approached on orbits that would bring them back again in the near future. These return visitors were logged carefully, their future paths extrapolated years ahead. None posed immediate danger, but their presence deepened the sense that the swarm was not a fleeting event, but the beginning of something ongoing. The question that hung over everything was simple but unresolved. Where were they coming from? If these were fragments of Atlas, why did their compositions vary so widely? If they were drawn from the asteroid belt, why now? If they were interstellar like Atlas itself, why were their orbits so inconsistent? Every explanation seemed incomplete. Every theory left gaps. The swarm was real, but its origins remained hidden, like the source of a river lost in darkness. The longer it continued, the harder it became to dismiss. By late in the year, the number of new detections had already surpassed records. Statistically, the odds of such clustering were infinitesimal, yet the data kept coming. For many astronomers, the experience was disorienting. They had spent careers treating the sky as a place of predictable order, governed by laws that yield to calculation. Now, confronted with a swarm of objects arriving in defiance of probability, they found themselves staring at equations that no longer comforted them. The swarm also forced a reconsideration of history. Were there earlier swarms we had missed? Could the great comet showers of the past, the unexpected meteor storms recorded centuries ago, have been the surface evidence of similar episodes? Some began re-examining old records, wondering if echoes of past swarms lingered in forgotten accounts of bright skies and falling stars. The idea that the multiplication around Atlas might not be unique, but part of a recurring pattern was both unsettling and oddly reassuring. If it had happened before, and Earth had survived, then perhaps survival was likely again. Yet the scale of the current swarm suggested something larger, something unprecedented. As Atlas itself glowed green against the stars, the swarm became its silent chorus. Dozens, then hundreds of bodies traced paths through the inner solar system, each one a reminder that the sky is far less empty than we pretend. To call them harmless was true in the narrowest sense, since none were on impact trajectories, but to see so many arrive at once was to feel a vulnerability that numbers could not erase. The swarm was not a single threat. It was the possibility of many, a constant reminder that the next detection could be the one that mattered. And so the swarm began, and with it a new chapter in how humanity sees its place in the cosmos. Not alone, not isolated, not safe in a system of predictable orbits, but surrounded by waves of wanderers, each one carrying with it the possibility of disruption. The sky had shifted. The swarm was here, and no one could say how long it would last, or what it meant for the future. As the swarm thickened around Earth and the strange green glow of Atlas dominated the night sky, the search for explanations turned toward gravity. If there was one force capable of shaping the cosmos on scales, from the smallest fragment to the largest galaxy, it was gravity. Every orbit, every resonance, every unexpected clustering of objects eventually traced back to its influence. Yet what astronomers began to see during this season suggested that gravity's hand was subtler, stranger, and perhaps more hidden than they had accounted for. On the surface, the idea was simple. Gravity is universal, predictable, and deterministic. Given enough data, every trajectory can be mapped, every orbit calculated. But in practice, the solar system is not a clean slate of equations. It is a chaotic environment, a place where countless small influences accumulate over time, nudging objects into unexpected paths. Jupiter alone reshapes the asteroid belt, shepherding some bodies into stable resonances while ejecting others into deep space. Saturn, Uranus, and Neptune add their own perturbations, as do Earth and Mars, even the Moon. The result is a web of gravitational interactions so complex that even with modern computing, predictions sometimes unravel. The multiplying objects around Atlas highlighted just how tangled this web could become. Some of the new arrivals trace back to the asteroid belt, their orbits showing evidence of long, slow evolution under the tug of giant planets. Others, more puzzling, seem to appear almost fully formed on Earth-crossing trajectories, as though they had been released from hidden reservoirs. The more closely astronomers examined them, the clearer it became that many had been delivered along pathways carved not by chance, but by invisible structures in the solar system's gravitational field. These structures are not visible in any telescope. They exist as mathematical constructs, solutions to equations that describe how objects move under the combined influence of multiple bodies. Known as invariant manifolds, they act like cosmic conveyor belts, guiding small bodies along predetermined routes. Spacecraft engineers have long exploited them, using these gravitational highways to slingshot probes across the solar system with minimal fuel. But to see so many natural objects apparently following similar routes suggested something deeper. The swarm was not simply random debris. It was being channeled, subtly but inexorably, by gravity's secret hand. One striking example came from an asteroid designated only weeks after discovery. Its orbit showed that it had passed near Jupiter decades earlier, a close encounter that had thrown it inward along a trajectory almost perfectly aligned with Earth's. Ordinarily, such encounters are rare and scattered, but in the months surrounding Atlas's approach, multiple objects showed similar histories, each one nudged at just the right moment to arrive near Earth now. The odds of this happening repeatedly, without some underlying structure, were vanishingly small. Some astronomers began to wonder whether the solar system itself was entering a phase of alignment, a temporary configuration in which gravitational resonances opened corridors more widely than usual. If so, then the swarm was not an anomaly but a natural outcome of celestial mechanics. Rare, but not inexplicable. Yet this explanation raised its own questions. Why should such a configuration coincide so neatly with Atlas's arrival? Was the interstellar visitor simply unlucky enough to appear during a moment of heightened traffic, or was there a connection between the two? Speculation flourished. A few proposed that Atlas itself, though too small to exert significant gravity, might have interacted with resonant populations of debris during its approach, disturbing them just enough to send fragments inward. Others suggested the influence of the sun's activity, with solar radiation subtly altering the orbits of comets and asteroids, amplifying gravitational effects in ways not yet fully understood. Still others, more radical, entertained the idea that interstellar tides, gravitational forces from the broader galaxy, might occasionally stir local populations into motion, funneling them inward in clusters. Each theory carried pieces of plausibility, yet none fully explained the scale of the swarm. The hidden hand of gravity was not limited to delivery. It also played tricks with perception. Objects arriving along certain pathways often did so with minimal warning, slipping in from directions where Earth-based telescopes struggle to see. Many approached from near the sun, their faint light lost in glare until they were almost upon us. Others swept in from high inclinations, crossing the plane of the solar system at sharp angles that defied traditional search strategies. These blind spots were not accidental. They were dictated by geometry, by the way Earth's orbit and the sun's brightness conceal vast portions of space from our gaze. Gravity guided objects into these hidden approaches, and by doing so, it reminded us of our vulnerability. The more data accumulated, the more the swarm looked less like chaos and more like orchestration. Not in the sense of deliberate control, but in the sense of a natural order hidden beneath randomness. Gravity was the conductor, drawing bodies inward along pathways invisible to the naked eye, but etched into the mathematics of motion. To see it play out in real time was both awe-inspiring and unsettling. Awe-inspiring because it revealed the depth of structure in the cosmos. Unsettling because it showed how little control we truly have. The public heard whispers of these ideas, though rarely the full detail. Media reports spoke of gravitational highways and invisible pathways, translating technical terms into metaphors that captured the imagination. The image of hidden corridors opened by the secret hand of gravity spread quickly. It was easy to grasp, easy to fear, easy to connect with the unease already stirred by the swarm. For many, the idea that objects could slip toward Earth along invisible routes felt more threatening than randomness itself. Randomness can be ignored, but hidden structures suggest inevitability. In professional circles, the debate became urgent. If gravity was indeed guiding these objects inward, then prediction required new models. It was no longer enough to calculate individual orbits in isolation. Instead, astronomers needed to map the larger structures, the resonances and manifolds that shape populations over time. Doing so would require immense computational effort, new surveys, and above all, new ways of thinking. The swarm was forcing a paradigm shift. Yet even as the models improved, uncertainty lingered. Gravity may be predictable, but chaos is embedded within it. Small differences in initial conditions can lead to wildly divergent outcomes, a reality known as the three-body problem. No matter how powerful the computers, no matter how precise the data, there are limits to how far ahead predictions can reach. The swarm embodied this paradox, guided by gravity yet unpredictable in detail, ordered in the large, chaotic in the small. A reminder that certainty in celestial mechanics has boundaries, and beyond those boundaries lies a fog of probabilities that even experts cannot fully penetrate. The hidden hand of gravity also sharpened the stakes for planetary defense. If swarms can be delivered along these pathways, then Earth may face not isolated threats but waves of them, compressed into short spans of time. A single asteroid can be deflected with planning, but dozens arriving together strain the system beyond capacity. Even without impacts, the psychological weight of constant near misses could destabilize public trust. The realization that gravity itself could conspire to deliver such waves was sobering in the extreme. As Atlas glowed against the backdrop of the swarm, the sense of orchestration deepened. It was impossible not to see the comet as part of the same structure, its interstellar trajectory intersecting with the gravitational skeleton of the solar system at precisely the moment the hidden pathways opened. Whether coincidence or connection, the timing was haunting. Gravity, indifferent and impersonal, had drawn together an interstellar wanderer and a swarm of local debris in a cosmic convergence that no one had predicted. And so, the story of Atlas and its companions became the story of gravity's secret hand. A force so familiar we take it for granted, yet so intricate that it shapes destinies across light years. The swarm was not random. It was sculpted, guided, channeled, and in its wake, humanity was left to reckon with the realization that the universe may be less chaotic than it appears, but also less forgiving. For hidden within the order is inevitability, and inevitability is a weight far heavier than chance. The multiplying objects had already unsettled astronomers, but the real weight of the situation settled in when the conversation turned to what could actually be done about it. For years, planetary defense had been presented as a problem with a solution. Given enough warning time, humanity could detect threats, track them, and if necessary, deflect them. The message was comforting, and for the most part, it was true. So long as threats arrived one at a time, on predictable paths, with years or decades of notice. The swarm shattered that illusion. The dilemma became clear almost immediately. The machinery of planetary defense was built around the assumption of scarcity. A dangerous object large enough to cause global damage is expected to appear only once in tens of thousands of years. Regional threats, smaller but still catastrophic, might be expected once every few centuries. Even smaller impacts, devastating locally, occur more often but still with gaps measured in decades. Systems were designed with this cadence in mind, calibrated to detect the rare, not the frequent. The swarm upended those expectations by delivering dozens of potential threats within weeks. Even if none of them were on collision courses, the workload alone strained the system. Every new detection had to be logged, tracked, its orbit refined, its probability of impact calculated. This process involves global coordination. Observatories handing off observations across time zones, radar facilities aiming beams at objects as they passed within range, data centers processing streams of numbers into orbital solutions. Under normal conditions, it is manageable. Under swarm conditions, it became overwhelming. The first part of the dilemma was technical capacity. Could humanity even track this many objects at once? The answer was uncomfortably close to no. Surveys raced to keep up, but blind spots remained. Objects approaching from near the sun went undetected until they were almost upon us. High inclination approaches slipped past standard search patterns, and the more crowded the sky became, the more difficult it was to prioritize which detections demanded attention. With limited telescope time and limited computational resources, choices had to be made, and each choice carried risks. The second part was response capability. Even if an object were found to be on a collision course, what could be done about it? The leading strategies involve kinetic impactors, spacecraft designed to slam into an asteroid and nudge it off course. The DART mission had already demonstrated the feasibility of this approach on a test asteroid, proving that momentum transfer works. But scaling that success to a real threat requires years of preparation. Designing the mission, building the spacecraft, launching it, and timing the impact precisely. The swarm offered no such luxury. Objects were arriving within days, weeks at most. There was no time to mount a deflection mission. The only options available were evacuation and mitigation, both limited in scope and effectiveness. The third part of the dilemma was psychological. For decades, planetary defense had reassured the public with the idea that threats were rare and manageable. The swarm demolished that narrative. Even though none of the objects were actually on collision courses, the constant stream of headlines created the perception of imminent danger. People began asking uncomfortable questions. Why are so many asteroids suddenly appearing? Why can't we stop them? What if one slips through? The fear was not entirely rational, but it was not baseless either. The more objects multiplied, the greater the odds that one would eventually pose a real threat. Governments struggled to respond. Some issued statements emphasizing that no impacts were predicted, but the reassurances sounded hollow in the face of daily announcements about new arrivals. Others called for accelerated investment in defense technologies, proposals that had long languished in bureaucratic limbo. For the first time, planetary defense was no longer an abstract policy discussion, but a pressing matter of public concern. Budgets were re-examined, committees convened, emergency plans dusted off, yet even as the machinery of government turned, the underlying dilemma remained. No amount of preparation could change the fact that the swarm was here now, and humanity was not ready. Scientists inside the planetary defense community felt the weight acutely. Many had dedicated their careers to building systems that offered reassurance, systems that gave humanity the illusion of control. To see those systems strained to the breaking point was sobering. Some admitted privately that the field had oversold its readiness, presenting planetary defense as further along than it really was. Others argued that the swarm, while alarming, was an anomaly and not reason to abandon the long-term approach. But in the heat of the moment, those distinctions mattered little. The public saw objects multiplying in the sky, and they demanded answers. The dilemma also carried a deeper layer. Even if humanity could build a perfect defense system, complete global coverage, instant detection, rapid response deflection technologies, it would not change the reality that the universe is bigger than our capacity to control it. A single swarm might be managed, but what if swarms are recurring? What if interstellar visitors routinely bring waves of debris in their wake? What if the galaxy itself is threaded with unseen streams of objects, any one of which could intersect our system without warning? No defense can prepare for an infinity of possibilities. The dilemma was not just about capacity, it was about humility. As the swarm thickened, these questions grew sharper. Astronomers logged object after object, each one harmless, yet each one a reminder of how thin the line is between safety and catastrophe. The defense systems held, but only barely, and only because none of the swarm objects happened to be on collision courses. It was a matter of luck, not preparation. Everyone knew it. The calculations could not hide the truth. The defences had not been tested against impact. They had been tested against volume, and the volume had nearly broken them. The dilemma extended beyond Earth itself. Satellites, the backbone of modern civilization, faced their own risks. Many of the swarm objects passed within the orbit of geostationary satellites, raising alarms about potential collisions. While the odds of a direct hit were low, the possibility forced operators to adjust orbits, burning fuel and shortening lifespans. In some cases, satellites were temporarily powered down to protect sensitive electronics from potential debris fields. The ripple effects were immediate: disruptions in communications, delays in weather forecasting, interruptions in global navigation. The swarm was not just a theoretical danger, it was already impacting daily life. This perhaps was the most sobering aspect of the planetary defense dilemma. The threat was not limited to rare extinction-level impacts. Even small disruptions could cascade into crises. A collision in low Earth orbit could generate debris fields that endangered hundreds of satellites. A strike in the ocean could unleash tsunamis devastating coastal populations. An airburst over a city could flatten infrastructure and kill thousands. The swarm made it clear that the spectrum of threat was broad, and humanity's defences were not calibrated for it. In the end, the dilemma was simple to state but impossible to resolve. How do you defend a planet when the threats multiply faster than your ability to respond? Detection alone was not enough. Deflection was too slow. Mitigation was too limited. The swarm forced a confrontation with the limits of human power. For all our technology, for all our knowledge, we remained vulnerable to the cosmos. Gravity's hidden hand could deliver objects at will, and all we could do was watch, calculate, and hope they passed us by. The dilemma lingered long after the first wave of the swarm subsided. It became a case study, a warning, a reminder that planetary defense is not a solved problem, but a fragile framework, one that depends as much on luck as on preparation. And as Atlas continued its approach, glowing green against the stars, the multiplying objects ensured that no one could forget the fragility of that framework. The defense of Earth, once a matter of reassurance, had become a matter of survival. The thing about swarms is that they don't stay contained. One object brushing past Earth can be dismissed, 2 or 3 can be tracked and explained, but dozens arriving in quick succession begin to create consequences of their own. Even without impact, the presence of so many bodies alters the balance of the inner solar system. The more astronomers studied the swarm around Atlas, the clearer it became that what was unfolding was not just a sequence of coincidences, but a chain of possibilities, each one linked to the next like falling dominoes. The idea is simple enough. Space is not static. Every close pass, every gravitational encounter, every subtle nudge has ripple effects that can cascade far beyond the moment. An asteroid skimming by Earth at a distance of a few 100,000 kilometers doesn't just pass harmlessly into the void. It exchanges momentum, however slightly, with our planet. That momentum alters its orbit, which in turn changes the encounters it will have years or decades from now. And if another asteroid happens to pass through a similar region, its trajectory too is shifted, the two influences combining in ways that can no longer be untangled. Each close pass is a push to the next, and the next, and the next. A domino falls, and the chain begins. The swarm magnified this reality in ways that had rarely been considered. Ordinarily, planetary defense focuses on isolated threats. An asteroid predicted to pass near Earth in 30 years, a comet calculated to cross our orbit in 75. Models are run, trajectories refined, impact probabilities calculated. But with dozens of objects arriving together, the system became dynamic in a way no one was prepared for. Their gravitational fields, individually small, collectively began to matter. Some nudged each other during distant passes, their orbits altered subtly but measurably. Others were influenced by Earth itself, their close approaches leaving them on new paths that guaranteed future returns. The dominoes were falling, and no one could predict where the chain would end. One particularly striking case involved a mid-sized asteroid that passed within lunar distance. Its trajectory had originally placed it on a harmless orbit, one that would not intersect Earth again for centuries. But the close pass altered its velocity by a fraction, just enough to shift its next approach into a window only decades away. What had been a non-threat suddenly became an object of long-term concern, and this was not unique. Several swarm members experienced similar perturbations, their futures rewritten by near misses that in isolation would have been trivial, but in combination carried significant weight. The domino effect extended beyond Earth. Mars experienced its own close encounters, as did Venus. Jupiter, as always, played the role of cosmic bouncer, deflecting some bodies outward, ejecting others into interstellar space, and occasionally sending them inward on new trajectories. Each interaction created consequences that rippled forward in time. Astronomers realized that the swarm was not just a temporary spike in activity. It was setting the stage for decades, even centuries, of altered orbital dynamics. The dominoes would keep falling long after Atlas itself had left the solar system. This realization unsettled the planetary defense community further. It meant that the risk horizon had shifted. Even if none of the swarm objects struck Earth now, their altered trajectories could make them threats in the future. Impact probabilities had to be recalculated not once but repeatedly. Each time new data refined the consequences of previous encounters. The domino chain was too complex to map fully. chaos theory guaranteed that small uncertainties in measurement would balloon into unpredictability within a few decades. The system was no longer a collection of isolated orbits. It was an interlinked web of cause and effect, one push leading to another in ways no one could control. The domino effect also raised questions about history. Could past impacts on Earth, the craters that scar its surface, the extinctions that punctuate its record, have been triggered not by isolated wanderers but by swarms like this one? Could ancient cascades of close passes have reshaped the trajectories of dozens of objects, sending one or two toward Earth after centuries of delay? If so, then the current swarm was not unique but part of a recurring cycle. A reminder that mass extinctions and planetary upheavals may not be the result of random chance alone but of long chains of cosmic cause and effect. As this line of thinking spread, the sense of unease deepened. The domino metaphor captured something essential about the human experience of risk. One event may seem manageable, but the chain it sets off is uncontrollable. Once the first tile falls, the rest follow whether we want them to or not. The swarm forced humanity to see the solar system not as a static environment, but as a dynamic one, filled with hidden chains of influence. Atlas had not just arrived, it had triggered a cascade that would echo far into the future. For the public, the idea of dominoes became both frightening and oddly familiar. People understood the concept of chain reactions, of small events snowballing into larger ones. The swarm provided a cosmic version of that story. News outlets spoke of how each asteroid's path could alter the next, how close calls today might mean collisions tomorrow. The sense of inevitability grew, even though astronomers emphasized that no immediate impacts were predicted. The psychology of dominoes is powerful. Once people see the pattern, they assume the chain will eventually end with disaster. Behind the scenes, scientists wrestled with the math. Orbital simulations were run endlessly, exploring thousands of possible futures. Some showed nothing more than harmless dispersal, the swarm fading back into the background noise of the solar system. Others showed darker outcomes, chains that led to one or more bodies striking Earth within decades. The probabilities varied wildly, but the uncertainty itself was unnerving. The domino effect did not offer neat answers. It offered a spectrum of possibilities, some safe, some catastrophic, all tangled together in ways no model could fully resolve. The metaphor stretched further still. Some argued that the dominoes were not only physical but cultural. Each detection triggered another wave of public anxiety, another round of government debate, another push for funding or preparedness. Each near miss eroded trust in reassurances, priming populations to expect disaster even when none was likely. The psychological dominoes fell in parallel with the physical ones, each feeding the other, until the sense of inevitability threatened to overwhelm rational discussion. What made the situation worse was that Atlas itself refused to fade into the background. Its green signal continued to glow, a constant reminder that the swarm was not occurring in isolation, but in the shadow of an interstellar visitor. The coincidence fed the perception that the dominoes were not random at all but orchestrated, whether by natural forces we do not yet understand or by something more deliberate. The idea of orchestration remained taboo in professional circles, but it thrived in the public imagination. To many, the dominoes did not just represent chance, they represented intent. In time, the domino effect forced a re-evaluation of planetary defense strategies. It became clear that systems designed for isolated threats were inadequate for swarms. That preparation had to include scenarios where multiple objects arrived together, their interactions altering future risks in unpredictable ways. This required new tools, new models, and above all, new humility. The dominoes reminded humanity that the cosmos is not static, that every action has consequences, and that those consequences can extend far beyond the moment. And so the swarm was no longer just a cluster of objects passing through. It was a cascade, a chain reaction, a sequence of dominoes stretching into the future, each one falling into the next, each one reshaping the system in ways too complex to fully grasp. Atlas had triggered a story that would not end with its departure. The dominoes would keep falling, and humanity could only watch, calculate, and prepare as best it could, knowing that somewhere down the line one of those falling tiles might land directly on Earth. The swarm by itself was unnerving, but what truly captured the imagination of both scientists and the public was the question of what would happen if even one object failed to miss. Close passes can be explained away as routine. Statistics can be wielded to show that most objects never strike, but the presence of so many bodies at once forced the mind toward darker possibilities. Among them, one scenario stood out as the most chilling: a direct hit in the oceans. The Earth is covered mostly by water. More than 70% of its surface lies beneath seas and oceans that stretch across basins thousands of kilometers wide. Statistically, this makes them the most likely target for any incoming asteroid or comet. If you imagine tossing darts at a globe, most of them land in blue. That simple truth is both comforting and terrifying. Comforting because a strike in the middle of an ocean spares cities and infrastructure from the initial blast. Terrifying because the energy released into water does not vanish, it transforms into waves. The physics of water impact is brutal. When an asteroid plunges into the sea at cosmic velocities, it transfers immense kinetic energy in an instant. A rock only a few hundred meters wide carries the force of thousands of nuclear weapons. The result is not just a crater, but a cavity blasted into the ocean itself. Water surges outward, then collapses back, sending towering waves racing across the surface. Unlike earthquakes that generate tsunamis through shifting seafloor, an impact delivers energy directly into the water column, creating waves far larger than anything tectonics can produce. Simulations of such events are sobering. A 1-kilometer asteroid striking the Atlantic could send waves hundreds of meters high toward every coastline bordering it. Cities on the eastern seaboard of the United States, the Caribbean islands, the coasts of Africa and Europe, all would face walls of water sweeping inland for tens of kilometers. Even smaller impacts are devastating. An object only a few hundred meters wide could erase ports, flood megacities, and cripple global trade. The water carries not just destruction but debris, ships hurled inland, oil facilities ruptured, nuclear plants overwhelmed. The aftermath would not be measured only in lives lost, but in economies collapsed and societies destabilized. The nightmare grows when you consider how little warning such an event might provide. Many of the swarm objects were detected only days before close approach. If one of them had been on a trajectory toward an ocean strike, there would have been no time for evacuation. The logistics of moving millions of people from coastal regions in less than a week are impossible. Even if warnings were issued, most would still be in place when the waves arrived. Survival would depend on geography and chance more than preparation. History offers glimpses of this nightmare. The Chicxulub impact that ended the age of dinosaurs struck shallow seas, generating waves that swept across the Proto-Gulf of Mexico. Geological records show deposits carried hundreds of kilometers inland, sediments churned by water moving at impossible speeds. More recently, smaller events like the 1908 Tunguska airburst over Siberia remind us that even non-ocean impacts release city-destroying energy. In 2013, the Chelyabinsk meteor exploded in the atmosphere, with a force of several nuclear bombs, injuring thousands through shattered glass alone. Scale these examples to an ocean strike, and the consequences are clear. The nightmare is not hypothetical. It is a matter of time and probability. The swarm made that probability feel uncomfortably real. Each detection raised the question, what if the next one does not miss? Models run by planetary defense groups often include scenarios of ocean impacts, but they're usually treated as low-likelihood events, studied more for completeness than urgency. Now, with objects multiplying in the sky, those same scenarios began to feel less like distant speculation and more like potential headlines. Simulations were rerun, maps of inundation produced, estimates of casualties recalculated. The numbers were staggering. Tens of millions could die in a single strike. Hundreds of millions could be displaced. Entire nations could be destabilized overnight. Beyond the immediate devastation, the ripple effects on the global system would be profound. Modern civilization depends on coastal infrastructure. Ports handle the majority of global trade. Refineries, power plants, and factories cluster near the sea. If waves hundreds of meters high obliterated those facilities, the supply chains that keep economies running would collapse. Food shortages, fuel crises, and political instability would follow. Even regions far from coastlines would suffer as trade ground to a halt. In a world already stretched thin, the secondary effects might be as deadly as the waves themselves. And then there is climate. An ocean impact injects vast amounts of water vapour into the atmosphere, along with debris blasted from the seafloor. Some models suggest this could trigger short-term cooling, similar to volcanic eruptions that shade the Earth with aerosols. Others warn of long-term warming if greenhouse gases are released in large quantities. The uncertainty adds another layer to the nightmare. Not only would the immediate destruction be catastrophic, but the climate system could be jolted into unpredictable states. For governments and defence planners, the scenario presented impossible choices. Even if an object were detected with enough warning to predict an ocean impact, what could be done? Evacuation on the necessary scale is unrealistic. Deflection requires years of preparation, not days. The only feasible action might be to move critical resources inland, a triage strategy that abandons millions to save infrastructure. No leader wants to face that decision. The swarm made it clear that such decisions might not remain hypothetical forever. Public perception of the nightmare grew quickly. Media outlets seized on the scenario, producing graphics of waves sweeping across familiar coastlines, simulations of cities submerged. Social media amplified the fear, spreading exaggerated claims alongside real science. The line between speculation and certainty blurred. People living in coastal regions began to ask what their governments would do, where they could go, how they could survive. The fear was visceral because it was grounded in geography. Everyone knows where the ocean is. Everyone can imagine the waves. Scientists tried to walk a careful line. They emphasized that no specific impact was predicted, that the probabilities remained low. Yet they could not deny the reality that the scenario was plausible. And with the swarm multiplying overhead, their reassurances carried less weight than usual. Numbers could not erase images of waves racing across continents. Probability could not silence imagination. The nightmare had taken hold, and once it did, it refused to let go. What made it worse was the realization that an ocean strike would not be a single disaster, but a global one. Unlike earthquakes or hurricanes, which devastate regions, an asteroid impact in the sea would send consequences in every direction. No coastline would be safe. Even landlocked nations would feel the effects as trade collapsed and refugees surged across borders. The world is interconnected in ways it has never been before, and that interconnection turns localized events into planetary crises. The nightmare was not just about waves, it was about systems unraveling. The swarm reminded humanity that its sense of security is fragile. We build cities at the water's edge, confident that the ocean is predictable. We invest in defences against storms and rising seas, assuming that those are the greatest threats we face. The multiplying object shattered that assumption. They forced us to see the ocean not as a buffer, but as a target, the most likely place where the cosmos would strike. The nightmare was no longer abstract. It was present in every orbital plot, every radar echo, every faint streak across the sky. And yet, amid the fear, there was also recognition of opportunity. The nightmare served as a catalyst, pushing governments to take planetary defense more seriously, to fund detection systems, to consider deflection technologies that had been neglected. The thought of waves sweeping away entire coastlines concentrated attention in a way no report or conference could. Fear, for once, became motivation. Whether that motivation would last beyond the immediate swarm was uncertain. But for a moment at least, the ocean impact nightmare forced humanity to confront the reality of its vulnerability. As Atlas continued its approach, glowing green against the crowded sky, the nightmare remained unspoken but omnipresent. Every new object added to the swarm carried the same silent question. What if this one is different? What if this one lands in the water? What if tomorrow the nightmare ceases to be a scenario and becomes reality? The ocean waited, vast and indifferent, covering most of the Earth's surface, and above it the swarm continued, dominoes falling in silence, each one a reminder that the nightmare was not only possible but inevitable, someday, if not today. If the nightmare of an ocean impact haunted coastal nations, the vision of an object striking over land was no less terrifying. For many, it was even worse, because the consequences were immediate, concentrated and personal. Cities are built to endure storms, earthquakes, even wars, but nothing in their design contemplates the sudden arrival of a rock from the sky, moving faster than a bullet, hotter than a furnace, more powerful than any weapon we have ever wielded. The swarm of objects arriving in the same season as Atlas forced humanity to think about that possibility not as abstract fiction, but as something that could happen with little or no warning. The difference between an ocean strike and an airburst over land is not in energy but in delivery. When an asteroid enters the atmosphere, friction heats it to incandescence. If it is small enough, it burns away entirely, producing nothing more than a streak of light across the sky. Larger objects, tens of meters across, survive long enough to explode in the atmosphere, releasing their energy in a blast wave that can flatten forests, shatter glass, or ignite fires. Larger still, those hundreds of meters wide can survive to the surface, releasing their energy directly on impact, excavating craters that swallow neighborhoods, districts, or entire metropolitan areas. The Chelyabinsk meteor in 2013 was a preview of what even a modest event can do. Entering the atmosphere at 19 kilometers per second, it detonated at an altitude of about 30 kilometers with the force of 500 kilotons of TNT. The shockwave shattered windows across 6 cities, injuring over 1,000 people. That rock was only about 20 meters across. Scale the size up tenfold, and the consequences magnify beyond comprehension. Buildings would collapse, infrastructure would crumble, entire districts could vanish in seconds. The Tunguska event in 1908 offers another sobering reminder. A body estimated at 50 meters in diameter exploded over Siberia, flattening 2,000 square kilometers of forest. Had it occurred over a city, the devastation would have killed millions. The swarm forced humanity to confront the possibility that such an event could repeat itself, not in remote wilderness, but over one of the densely populated urban centres where billions now live. The dilemma of urban impact is compounded by unpredictability. Ocean strikes at least produce waves that spread energy outward, hitting coastlines with some delay. Airbursts and surface impacts over cities are instantaneous. Warning time is measured not in hours but in seconds, if at all. Even if astronomers detected an incoming object days before, the uncertainty in its path might not allow prediction of the exact target until it was too late to evacuate. The swarm heightened this sense of vulnerability. With so many new detections arriving with little warning, the odds of one targeting a city by chance could no longer be dismissed out of hand. The consequences of such an event go far beyond immediate casualties. Modern cities are hubs of global systems. They house financial centres, government institutions, industrial complexes, communication infrastructure. The destruction of one megacity would ripple across the world. If New York were struck, the financial system would convulse. If Tokyo, the global supply chain for technology would fracture. If Shanghai or Mumbai, The economic and demographic shock would destabilise entire regions. A rock only a few hundred metres across, striking in the wrong place, could alter the trajectory of civilization. Simulations of city impacts are chilling. Models show shockwaves moving faster than sound, shattering buildings across tens of kilometres. Thermal radiation ignites fires across entire metropolitan areas. Dust clouds rise into the atmosphere, plunging the region into darkness for days or weeks. Survivors, if any, face shortages of food, water and medical care. Rescue efforts falter as infrastructure collapses. The scale of death is immediate, but the scale of suffering extends long after the blast. The swarm also raised questions about secondary consequences. A strike on a city built near chemical plants, refineries, or nuclear facilities would unleash additional disasters: fires, explosions, radioactive contamination. A hit near dams or reservoirs could trigger floods. Urban density amplifies every risk, turning what might otherwise be a regional event into a catastrophe of global proportions. And then there is psychology. Humanity has grown accustomed to thinking of cities as bastions of safety, places where life is controlled, predictable, governed by rules and technology. The thought that a single rock could erase all of that in seconds is destabilizing in a way numbers cannot capture. The image of fireballs streaking through the sky above skyscrapers, of shockwaves shattering glass across towers, of streets swallowed by craters, those images cut deeper than statistics. They lodge in the imagination, and once they are there, they are hard to dislodge. The swarm ensured those images circulated widely. News reports began to highlight not just the frequency of detections, but the possibility of urban strikes. Graphics showed asteroids superimposed over maps of cities, illustrating the scale of destruction. Social media filled with videos of Chelyabinsk and simulations of larger events, spreading fear faster than scientists could counter it. The phrase "city killer" entered headlines, shorthand for asteroids large enough to obliterate urban centres. Once the phrase took hold, it stuck. Behind the scenes, governments quietly began to prepare. Emergency agencies drafted plans for impact scenarios, though they knew full well that most were unworkable. Evacuating a city of 10 million in days or hours is impossible. Sheltering populations underground is impractical. In truth, there is no defence against a direct hit on a city. At best, warnings could save those lucky enough to flee in time, but most would be left to chance. The swarm made that reality harder to ignore. Scientists faced their own dilemma. They could not minimise the risks without undermining trust, but they could not amplify them without fueling panic. The balance was delicate. Some argued for transparency, publishing every detection and probability. Others argued for restraint, fearing that constant warnings would desensitise the public or erode confidence. The swarm forced the issue, as detections piled up faster than communication strategies could adapt. The public learned in real time just how thin the line between safety and disaster had become. The prospect of city strikes also reshaped debates about planetary defence. If deflection technologies require years of preparation, then they are useless against objects detected days before impact. That leaves only mitigation. But what does mitigation mean for cities? Sheltering populations underground, relocating governments, decentralising infrastructure. Each solution raised new challenges, each more impractical than the last. The swarm underscored the grim reality. Prevention is possible only with early detection, and early detection is not guaranteed. The thought of skyfire over cities became a symbol of the larger crisis. It represented the vulnerability of modern civilization to forces beyond its control. It reminded people that for all our technology, we remain fragile, perched on the surface of a planet in a universe filled with wanderers. The swarm was a wake-up call, not because any one object was destined to strike, but because it revealed how unprepared we are if one ever does. As Atlas continued its inward path, glowing green in the darkness, the possibility of urban catastrophe remained unspoken but ever present. Each new detection forced the question, what if it were this one? What if tomorrow, instead of harmless passage, one of those streaks in the sky descended over a city, releasing its energy in an instant, turning the night into day and the world into chaos? The swarm offered no answers. It only offered possibilities, each one darker than the last. And so the image of skyfire over cities lingered, not as prophecy, but as potential, a nightmare waiting in the wings of probability. The swarm had opened the door to that nightmare, and once opened, it could not be closed again. From the first days of Atlas's detection, its colour drew attention, but colour was only the surface of the deeper story. Light carries information. When that light is spread into a spectrum, every dip and peak becomes a signature, every emission line a clue to the chemistry within. Astronomers learned to read those patterns long ago, turning telescopes into instruments not just of sight, but of analysis. And as they studied Atlas, what they found in its spectrum looked less like ordinary cometary behaviour and more like a coded message written in chemistry. Comets in our system are time capsules of the early solar nebula. Their gases reveal water, carbon dioxide, methane, ammonia, sometimes exotic molecules like cyanogen or formaldehyde. These ratios vary but usually fall within ranges that fit the story of our own planetary nursery. With Atlas, the numbers didn't fit. Early spectrographs showed unusually high levels of diatomic carbon, enough to produce the vivid green glow long before such emissions normally peak. Yet the water signature, which should have dominated, was faint. The balance was inverted. It was as if Atlas had been built in an environment where carbon reigned and water was scarce. As data accumulated, more anomalies appeared. Nickel and cobalt lines appeared in concentrations too high to ignore. Normally such metals are buried deep inside bodies, not shed freely in the coma. Their presence suggested either a different structure, perhaps metallic inclusions scattered throughout the nucleus, or processes we don't yet understand. Even stranger were hints of isotopic ratios that diverged from what is common here. Hydrogen deuterium levels, oxygen isotope distributions, traces of nitrogen compounds, all pointed to origins in a stellar nursery unlike our own. Atlas was not just foreign in space, it was foreign in chemistry, carrying within it the fingerprint of a different star's environment. To some, this was exhilarating. Here was evidence of how diverse planetary systems could be, proof that the galaxy is full of worlds shaped by different recipes, different balances of elements and ices. Atlas was a messenger, bearing physical samples of those alien conditions across light years. But to others, the anomalies carried unease. The swarm was already straining the imagination, and now the comet itself seemed to whisper that it came from somewhere stranger, less familiar, harder to place. The green glow became more than a curiosity. It became a signal, not intentional, but one that demanded interpretation. Chemistry has always been humanity's way of decoding the universe. Spectroscopy revealed helium in the sun before it was discovered on Earth. It uncovered the expansion of the cosmos in the redshift of galaxies. It told us about black holes, stellar nurseries, the atmospheres of exoplanets. Now it told us something unsettling about Atlas, that it was built in a place where the chemistry of life as we know it might be impossible, or alternatively a place where chemistry could have taken paths we cannot yet imagine. The green signal was not just a glow. It was a message that the galaxy is stranger, more varied and less predictable than we want it to be. The phrase, messages in chemistry, spread quietly among researchers, not as poetry, but as shorthand. Every line in the spectrum was a syllable, every ratio a phrase. The comet was speaking, not with intent, but with the inevitability of physics, and what it was saying was that we are not alone in the sense of isolation. We are part of a larger chemical conversation, one in which each visitor carries a fragment of some other world's story. Atlas spoke in a dialect no one had heard before. The anomalies deepened as more instruments were turned toward it. Infrared data showed organic molecules with unusual branching structures, compounds that do not fit neatly into our catalogue. Ultraviolet readings suggested unexpected levels of carbon monoxide, again out of proportion to water. The nucleus seemed porous, shedding gas in bursts that carried fragments of dust rich in metallic elements. Each new observation widened the gap between Atlas and comets of our system. The differences were not small. They were categorical. Atlas was other, in the truest sense. This realization carried implications beyond science. If chemistry encodes environment, then Atlas told us about a star system where ratios of elements were skewed, where heavy metals were abundant, where water was less common. What kind of worlds form in such a place? What kind of atmospheres? What kind of oceans, if any? The mind could not help but wander further. Could such chemistry support life? If so, would it resemble anything we recognize, or would it be so alien as to defy comparison? The message in chemistry was not just about elements, it was about possibility. The public seized on the mystery. Articles spoke of alien chemistry, of messengers from other stars carrying secrets of life's potential. Some speculated that Atlas might even carry biological signatures, frozen remnants of microbial ecosystems that evolved under strange suns. Scientists were quick to temper such speculation, reminding everyone that no evidence of biology existed. But the gap between what was known and what was possible left plenty of room for imagination. The green glow became not just a chemical curiosity, but a symbol of cosmic diversity. Within the planetary defense community, the chemistry raised different concerns. If Atlas was different in composition, then its structural strength, its density, its behavior under stress might also be different. Deflection strategies developed for icy comets or rocky asteroids might not apply. A body rich in metals could resist impact. A porous structure could fragment unpredictably. The swarm had already exposed weaknesses in preparedness. Now Atlas itself underscored that even the physics of deflection could not be taken for granted. Chemistry was not just a message, it was a complication. Behind the data and debates, there was a quieter truth. The messages in chemistry reminded humanity of its smallness. For centuries we imagined our solar system as the template, our chemistry as the standard. Atlas shattered that illusion. It carried within it the fingerprint of another world, another star, another history. The swarm around it emphasized the vulnerability of our planet. Together, they painted a picture of a cosmos where Earth is not central, not typical, not protected. Just one place among many, vulnerable to visitors and surprises we can neither predict nor control. As Atlas drew closer, the green glow intensified. The chemistry revealed itself in sharper detail, and the messages grew louder. No one could read them fully, not yet, but their meaning was clear enough. The universe is full of stories written in molecules, and each visitor carries a different one. The swarm was a chorus of trajectories, Atlas a single voice of chemistry, and together they said the same thing. The cosmos is wider, stranger, and more connected than we have ever believed. And with every passing night, as telescopes recorded new lines in its spectrum, the message deepened. Not an intentional signal, not a warning or greeting, but a reminder. The universe speaks in chemistry, and we have only just begun to listen. Every observation of Atlas pointed to one conclusion. This object was not made here. Its chemistry, its orbit, its green signal, its timing, all of it insisted that its story began far beyond the boundaries of our solar system. The swarm of objects that seemed to accompany it was disturbing enough, but the real gravity of the moment lay in what Atlas itself represented. For the first time, humanity was staring directly at material that had travelled across interstellar space for perhaps millions, maybe billions of years, and that meant confronting the question of origins in the galactic deep. The phrase itself carries weight. The galactic deep is not a place we can map with certainty. It is the vast expanse between stars, an ocean of darkness scattered with clouds of gas, threads of dust, and occasional wanderers set adrift when worlds collide or systems destabilize. Most of it is empty in the human sense, void of heat and light, filled only with particles thinner than the best vacuums we can create on Earth. Yet within that emptiness lies history. Every fragment that leaves a star system carries with it the fingerprint of its birthplace, encoded in chemistry, density, and structure. Atlas was one such fragment, and for the first time we could read its record with detail. Tracing its origin required more than orbital mechanics. Its hyperbolic trajectory confirmed interstellar entry, but that only narrowed the possibilities to infinity. It could have come from any star in any direction, ejected long ago by gravitational encounters or planetary collisions. Yet subtle clues hinted at more. Its velocity relative to the Sun placed it near the median speed of stars in the local galactic neighbourhood, suggesting it was not a rare outlier but part of the ordinary traffic of interstellar debris. That made it representative, not exceptional, and that was its own revelation. The galaxy is not just filled with stars and planets, it is filled with fragments like Atlas, drifting endlessly, waiting to cross paths with new systems. The chemistry told a deeper story. Ratios of carbon to oxygen, hydrogen isotopes and metallic inclusions all pointed to a place richer in heavy elements than our own. That suggested a star system born later than the Sun, forged in a region of the galaxy where earlier generations of stars had already seeded the interstellar medium with metals from their deaths. In that sense, Atlas was younger than Earth, even though it had travelled across unimaginable distances. It was the child of a star that had lived and died elsewhere, part of a lineage foreign to our skies. Speculation grew about what kind of system could have produced it. Was it born in the outer disk of a star like our own, shaped in a cometary reservoir before being thrown outward by a passing giant planet? Or was it a fragment of something more violent, torn loose when worlds collided, ejected into space by energies that destroyed its home? Every possibility carried implications. If it was a comet, then it represented the normal processes of planetary formation occurring everywhere. If it was a fragment of catastrophe, then it suggested a galaxy filled not only with creation, but with destruction. Every visitor a survivor of chaos. The galactic deep is not uniform. Stellar nurseries cluster in spiral arms. Molecular clouds stretch like filaments, and supernovae leave behind expanding shells of gas that seed the void with heavier elements. Somewhere in that tapestry, Atlas began its journey. Its chemistry was a breadcrumb trail, pointing back not to a specific star but to a type of environment, rich in carbon, poor in water, scattered with metals. It may never be possible to name its birthplace, but it was possible to imagine the kind of worlds that might have formed there. Perhaps dry planets with carbon-rich surfaces, perhaps atmospheres thick with hydrocarbons instead of oxygen, perhaps oceans of methane instead of water. Each speculation underscored the alienness of Atlas, the fact that it was not just a visitor, but a messenger from an entirely different kind of world. The swarm complicated the picture. Were the multiplying objects part of Atlas's origin, fragments ejected along with it from the same system? Or were they local debris stirred into motion by its passage? The answer remained elusive, but the timing of their appearance gave weight to the idea that Atlas was not alone in its journey. Streams of interstellar debris may travel together, stretch thin over light years, but arriving in clusters when they intersect a star system. If so, then Atlas was the vanguard of a larger flow, a river of fragments flowing invisibly through the galactic deep. The swarm was not coincidence. It was evidence of a structure we had never noticed before. To the public, the idea of the galactic deep captured imagination. Headlines spoke of wanderers from distant stars, of alien fragments carrying secrets of their birthplaces. The green glow became a symbol of that distance, a visible reminder that Atlas had crossed interstellar voids to reach us. For scientists, the fascination was no less profound, though grounded in data. Every molecule released from its coma was a sample from another system, a gift no probe could ever deliver. In a sense, Atlas brought with it the first physical evidence of worlds beyond our own, and it did so without intention, without message, without purpose. That absence of intent made it no less powerful. The galactic deep also reminded humanity of its own fragility. Earth is a single world orbiting a single star, but the galaxy contains hundreds of billions of stars, each with its own potential for planets, comets, and catastrophes. Atlas was one among countless fragments drifting through that ocean. The fact that it happened to cross our system in this moment was chance, but the larger truth was not. We live in a galaxy alive with motion, every star a source of debris, every system connected to the void. The swarm underscored that connection in the most unsettling way possible. Some voices raised darker possibilities. If Atlas was not unique, then streams of interstellar debris might crisscross the galaxy constantly. If so, then Earth's encounters with such streams are not anomalies but inevitabilities, recurring events across deep time, the great extinctions of the past, the scars etched into our planet's crust, may have been triggered not just by local wanderers, but by fragments from stars long gone. The galactic deep is not empty, it is active, shaping histories across countless worlds. In quieter corners of the debate, another question emerged. If debris like Atlas carries chemistry from other systems, could it also carry biology? Microbes frozen in ice, spores preserved in carbon, fragments of life waiting to seed new worlds. The idea of panspermia is ancient, and though evidence remains elusive, the arrival of an interstellar visitor reignited it. Perhaps Earth itself was seeded by such wanderers long ago. Perhaps Atlas was part of the same process, carrying the raw materials of life across the galaxy. The chemistry did not confirm it, but it did not rule it out either. In the silence of the galactic deep, such possibilities remain open. As Atlas approached the inner system, these questions grew sharper. Its green glow brightened, its spectrum revealed more detail, its presence became undeniable. And through it all, the message remained the same. This is not a comet like any you have seen before. This is a fragment of the galaxy itself, shaped by forces and histories beyond your own. The swarm around it was a reminder of vulnerability, but Atlas itself was a reminder of connection. Every system gives birth to wanderers, every star contributes to the deep, and sometimes those wanderers arrive carrying messages written in chemistry, trajectories, and presence. The galactic deep is vast beyond comprehension, but Atlas made it immediate. It was no longer an abstract expanse measured in light years. It was a body glowing in our sky, a visitor we could see, measure, and track. Its presence collapsed the distance of the galaxy into something tangible, something we could not ignore. And in doing so, it forced humanity to confront not just its vulnerability, but its place in a cosmos far larger, older, and stranger than it had ever dared to imagine. The more astronomers tried to understand why Atlas had arrived with such uncanny timing, the more they began to think not in terms of isolated events, but in terms of patterns. The swarm, the green signal, the strange orbits that seemed to appear out of nowhere. Taken alone, each could be explained, at least in principle. Taken together, they hinted at something broader. And in the background of those discussions, one idea kept surfacing, that the galaxy itself might be threaded with routes invisible to the eye, paths along which interstellar objects travel more easily than others, a hidden network of motion shaped by gravity and time, an interstellar highway. The term had floated around before, used metaphorically in discussions of how stars and their debris interact. but Atlas forced it into sharper focus. Its orbit, when traced backward, did not point cleanly to a single star, but to a broader region of galactic space where multiple streams of stellar motion overlap. Its velocity was not extreme but moderate, aligned with the average drift of stars near the Sun, and its chemistry, though alien, was not wildly so, suggesting it came from a place not unimaginable, but simply different. All of this hinted that Atlas had not been flung randomly into the void, but that it might belong to a broader traffic of objects moving through interstellar space along pathways as old as the galaxy itself. The concept of an interstellar highway begins with gravity. Stars are not fixed points, but move in orbits around the galactic centre, carrying with them comets, asteroids, and fragments born in their systems. Over billions of years, encounters between stars scatter debris outward. Planets fling objects away. Binary stars disrupt orbits. Supernovae blast fragments into space. Most of these wanderers drift aimlessly, but some find themselves caught in larger currents. Their paths shaped not only by the gravity of individual stars, but by the combined influence of the galaxy's structure. Spiral arms, molecular clouds, clusters of stars, all of these create regions where debris is more likely to concentrate, more likely to travel together. The idea is not unlike ocean currents on Earth. Water molecules move randomly, yet together they form streams that carry ships across great distances. In the same way, fragments ejected from countless stars may, over time, form flows through the galaxy, invisible rivers of rock and ice. When such a river intersects a planetary system, the result could be what astronomers now saw: a surge of object arriving in clusters, a swarm guided not by coincidence but by cosmic traffic. If that is true, then Atlas was not alone. It was part of a flow, a caravan of interstellar debris stretched across light years, perhaps centuries apart in arrival, but bound by a common origin. The swarm of objects that seemed to multiply around its passage might have been fragments from that same river, their trajectories warped into Earth-crossing paths as they slipped into the Sun's gravity well. To see so many at once was to glimpse the larger pattern. The interstellar highway had touched our system, and traffic was pouring in. For scientists, the implications were profound. If such highways exist, then interstellar visitors are not rare anomalies, but inevitable encounters. Every few centuries, perhaps every few millennia, Earth may pass through one of these streams, experiencing swarms of arrivals that alter its history. Some may pass harmlessly, as this swarm seemed to, others may not. The great impact that ended the dinosaurs' reign might have been one such event, triggered not by random chance but by Earth's crossing of a cosmic current. If true, then the planet's history is tied not only to local dynamics, but to the larger architecture of the galaxy itself. The interstellar highway concept also reframed how humanity thought about exploration. For decades, the dream of travelling to other stars has been limited by distance, by the sheer emptiness of the void. But if the galaxy contains streams of debris flowing between systems, then those streams are not empty. They are filled with material from distant worlds, fragments that carry information without ever requiring spacecraft. Studying them becomes a form of interstellar exploration, a way of sampling alien chemistry without leaving the solar system. Each visitor is a probe launched by nature, a messenger carrying data across incomprehensible spans of time. Of course, the term highway carries connotations of order, of direction, of deliberate construction. Scientists were quick to emphasize that no such order existed. The streams, if they exist, are statistical, not intentional. They are carved by gravity, not design. But language matters, and the phrase caught on precisely because it made the abstract tangible. People could imagine highways in space, lanes of motion carrying travellers from system to system. The metaphor gave shape to the unease stirred by the swarm. It was no longer just random multiplication, it was traffic, and traffic implies that more is coming. The data began to suggest as much. Orbital reconstructions of some swarm objects showed similarities in velocity and inclination, enough to hint that they had entered the solar system along related paths. Though their individual orbits diverged once captured by the Sun's gravity, their entry conditions lined up more than chance alone would predict. It was not proof, but it was suggestive. The interstellar highway was no longer just an idea. It was a hypothesis with growing support. The public seized on it quickly. Media outlets spoke of alien highways threading the galaxy, of invisible lanes carrying fragments from star to star. The narrative spread because it resonated. Highways are familiar, a way to understand something that otherwise defies comprehension. And in that metaphor, people found both wonder and dread. Wonder, because it meant the galaxy is alive with motion and connection. Dread, because it meant Earth is not a quiet outpost, but a stop along a route that may deliver catastrophe as easily as curiosity. Behind the scenes, the idea sparked debates about frequency. If Atlas is part of a stream, how often do such streams intersect our system? Are we in the midst of a rare event, one that happens only once in millions of years, or are we simply seeing for the first time what happens more often than we ever realized, thanks to new telescopes capable of catching faint visitors? The answer mattered, because it shaped how humanity thought about risk. A rare encounter could be dismissed as anomaly. A common one demanded preparation. The swarm made it harder to choose the safer answer. The interstellar highway also carried implications for the search for life. If streams of debris carry chemistry from one system to another, then the galaxy is not a set of isolated worlds but a network. Material exchange could spread complex organics, perhaps even life itself, across vast distances. Panspermia, long dismissed as speculation, gained new plausibility. Each fragment, like Atlas, could be more than just rock and ice. It could be a seed, drifting until it finds fertile ground. Whether those seeds ever take root is unknown, but the possibility cannot be dismissed. The interstellar highway could be not just traffic, but a distribution system for the ingredients of life. As Atlas brightened in the sky, glowing green against the stars, the metaphor of the highway grew harder to ignore. It explained too much, tied together too many threads. The swarm, the chemistry, the timing. Whether or not it was the full truth, it was a framework that made sense of the unease. The solar system had not been singled out for randomness. It had been intersected by a stream, a current flowing through the galactic deep. Atlas was just one of many travellers. The swarm was the toll of crossing paths. And humanity for the first time realised it might be living on the shoulder of a cosmic highway it had never noticed before. The story of Atlas and the multiplying objects was not just about comets and asteroids. It was also about the people watching them, the network of telescopes and instruments stretched across the Earth and orbiting in space, tasked with keeping an eye on the sky. For decades, this machinery of vigilance has been quietly scanning the heavens, logging faint dots of light, calculating orbits, and building a map of potential hazards. The system was built with patience in mind, the slow accumulation of data. But the swarm changed the rhythm. Suddenly, the watchers themselves became part of the story. Every discovery begins the same way. A faint dot shifts position slightly between exposures, standing out against the fixed background of stars. At first glance it looks meaningless, but to the trained eye it is motion, and motion is everything. Astronomers at survey facilities have grown used to the rhythm. Capture, compare, confirm, report. Most of the time the dots are familiar. Asteroids long catalogued, harmless comets returning on schedule. Occasionally something new appears, but rarely had new discoveries come at the pace seen during Atlas's approach. The watchers were overwhelmed. Rubin Observatory in Chile, Pan-STARRS in Hawaii, Catalina in Arizona, space-based platforms like NEOWISE, all of them began producing detections faster than they could be confirmed. Software flagged dozens of moving objects every night, each one demanding human verification. Teams worked around the clock, chasing faint points across the sky, feeding coordinates into orbital models, trying to keep pace with the flow. The feeling was not one of triumph, but of exhaustion. The sky was busier than it had ever been, and the machinery of vigilance strained under the weight. Behind the scenes, there was tension. The Watchers knew their systems were not built for this. Algorithms designed to filter noise were discarding real objects, simply because the flood was too intense. Others flagged so many false positives that valuable telescope time was wasted. The human element became critical again, scientists staring at digital images, deciding by eye which streaks were real. In an age of automation, the swarm dragged observation back into the realm of fatigue and judgment. The Watchers were no longer detached analysts. They were firefighters racing to keep up with sparks raining from the sky. The public rarely sees this side of astronomy. Headlines speak of discoveries as if they appear effortlessly, the product of smooth machines and confident calculations. In reality, discovery is messy. It involves uncertainty, corrections, endless cross-checking. During the swarm, the mess became visible. Some objects were announced as potential hazards, only to be downgraded hours later as better data refined their paths. Others were missed entirely, detected only after they had already passed close by. The Watchers knew this was inevitable, but to the public it looked like inconsistency. The more they watched the Watchers, the more they realised how fragile the system was. This fragility became part of the dilemma. Planetary defence depends on trust. The public must believe that scientists can detect and warn of threats in time, but the swarm exposed the limits of that trust. Watching the Watchers revealed just how much of the system is held together by long hours, imperfect algorithms and thin budgets. It was not a flawless shield. It was a patchwork, effective enough most of the time but vulnerable to overload. The multiplying objects brought it dangerously close to that point. Inside the community, the mood was conflicted. There was pride in what the Watchers had accomplished. The sheer number of detections proved the system worked. But there was also fear. If even one dangerous object had slipped through during the swarm, the consequences could have been catastrophic, not because of the rock itself, but because it would have destroyed trust. A missed detection, leading to an unexpected impact, would not only cost lives, it would shatter the credibility of the entire system, and once that trust is lost, it is nearly impossible to regain. The swarm also highlighted disparities. Not all Watchers had equal tools. Wealthy nations with advanced observatories contributed the most data, while others relied on what was shared through international networks. Coordination was good, but not perfect. Delays in communication sometimes meant objects were tracked hours later than they should have been. Political realities shaped what data was shared and when. For a threat that knows no borders, the unevenness of response was glaring. Watching the Watchers revealed not just dedication but also inequality. The situation raised another unsettling layer. Who is watching the Watchers themselves? In theory, peer review and open data keep the system honest, but in practice, much depends on a small community of experts, trusted to interpret faint signals from the sky. The swarm forced a reconsideration of oversight. If the Watchers are strained to their limits, who ensures that mistakes are caught? Who verifies that priorities are set correctly? In times of calm, these questions remain academic. In times of crisis, they become urgent. For the public, the human side of the Watchers began to show. News outlets interviewed exhausted astronomers, their voices cracking as they described the flood of detections. Images of glowing monitors in control rooms spread online. The Watchers hunched over keyboards late at night. Suddenly, the machinery of vigilance was no longer invisible. It was people, ordinary in every sense except for the extraordinary responsibility they carried. Watching them made the threat feel more real, not less. The vulnerability of the system mirrored the vulnerability of the planet itself. Amid the strain, there was also resilience. Teams collaborated across continents, handing off targets from one observatory to the next, chasing faint dots around the globe. Amateur astronomers joined in, filling gaps with backyard telescopes, proving once again that the line between professional and citizen scientist is thin in times of need. The watchers, for all their exhaustion, kept going. Every detection was logged, every orbit refined, every close pass noted. The swarm did not break the system, but it revealed just how close to breaking it could come. The experience left lasting marks. The watchers began pushing harder for upgrades, more telescopes, more automation, better algorithms. Governments, jolted by the public attention, showed signs of listening. Budgets that had once been small and symbolic now looked inadequate. The swarm had done what years of advocacy could not. It had shown in real time that the watchers are all that stands between humanity and the unknown, and if they falter, everyone pays the price. As Atlas continued its journey, glowing green in the night, the watchers followed every movement. The swarm objects crowded their databases, each one demanding attention. But behind the numbers there was a larger truth. The system of vigilance is fragile, human, and imperfect. Watching the watchers revealed not invincibility but strain, not flawless control but determined effort. And in that revelation lay both comfort and unease. Comfort because the watchers are dedicated beyond measure. Unease because dedication is not enough when the cosmos decides to press its advantage. The watchers kept looking up because they had no choice. And those who watched them, the public and the governments suddenly aware of their importance, realized that vigilance itself is fragile and that the sky is never as empty as it seems. The thought hovered at the edges of the conversation from the moment Atlas was first noticed, but no one dared voice it loudly at first. It was too easy to sensationalize, too easy to slip into science fiction when the stakes demanded sober observation. Yet, as the swarm thickened, as the green signal glowed brighter, and as chemical signatures refused to settle into familiar categories, the speculation became unavoidable. Was this truly just another fragment of cosmic geology? Or could it represent something more? Alien technology or natural wonder? Those were the two poles of the debate, and between them stretched a spectrum of uncertainty that no one could fully cross. The precedent had been set years earlier with Oumuamua. Its strange shape, its unexplained acceleration, and its silent departure left the door open to interpretations that unsettled many and excited others. Some argued that it was a fragment of a shattered planet. Others suggested exotic ice sublimating in ways not previously modelled. But a few dared to wonder if it might have been a probe, a relic of another civilization passing through without revealing itself. That debate never ended, and in many ways Atlas reignited it, bringing it back into the light at the worst possible time. The case for natural wonder was strong. The galaxy is vast, filled with billions of stars and countless systems where planets form and die. Every one of those systems produces debris, fragments that are flung outward into the interstellar void by gravitational encounters and collisions. Over billions of years, the number of such wanderers is unimaginable. That some of them should find their way into our solar system is inevitable. To assume every anomaly must be artificial is arrogance. The natural world is strange enough to explain most mysteries. Atlas, with its green glow and unusual chemistry, could easily be another such case, a product of conditions unlike those in our solar system, but natural nonetheless. And yet, the timing of the swarm troubled many. Natural processes are not expected to produce sudden flurries of arrivals clustered around a single interstellar visitor. The sheer multiplication of detections, the odd inclinations, the suggestion of hidden corridors, all of it created a context where speculation flourished. To some, Atlas looked less like an isolated comet and more like the lead car in a convoy. If that convoy were natural, it implied a hidden river of interstellar debris intersecting our system. If it were not, then the possibilities became more unsettling. The idea of alien technology has always been shaped as much by psychology as by science. When confronted with the unfamiliar, humans reach for the analogy that fits their imagination. Strange shapes become spacecraft. Odd accelerations become propulsion. Glows become signals. Skeptics counter that this is projection, the imposition of human narratives on indifferent phenomena. But the possibility cannot be dismissed entirely. After all, we know life exists in at least one place in the universe. We know intelligence exists here. To assume it exists nowhere else is as unscientific as assuming every anomaly must be evidence of it. The middle ground is uncertainty, and Atlas thrived in that uncertainty. The green glow in particular fed speculation. To most astronomers, it was explained by diatomic carbon fluorescing under sunlight. But the intensity, the timing, the ratio of gases, it did not quite fit. Some wondered aloud, cautiously, whether it could be artificial. Could it be the byproduct of controlled processes, the exhaust of some technology, the residue of something more deliberate? The data did not confirm such an idea, but neither did it completely exclude it. And in that narrow gap between certainty and doubt, imagination took root. The swarm objects themselves added fuel. A handful of them were elongated in shape, tumbling in ways reminiscent of Oumuamua. Others displayed activity inconsistent with comets of similar size, faint comae appearing and vanishing unpredictably. To a scientist, this was data demanding better models. To the public, it was evidence of strangeness, perhaps even intention. The line between natural and artificial blurred in perception, even if the science leaned toward nature. What made the debate so difficult was the scale of what was at stake. To declare Atlas, or any part of the swarm artificial, would be revolutionary, perhaps the most important discovery in history. It would mean we are not alone, that technology has existed elsewhere in the galaxy, and that fragments of it have crossed into our skies. But to leap to that conclusion prematurely would be equally catastrophic, undermining credibility and distracting from the real work of understanding. The watchers were caught in the middle, aware of the temptation to speculate, but bound by the discipline of data. Behind closed doors, however, the conversation was less restrained. Some researchers whispered about oddities in the data that had not yet been published. Patterns in the chemical ratios, fluctuations in the glow, the possibility of resonance among some of the swarm orbits. Each oddity by itself was explainable, but together they formed a picture that felt less like random geology and more like design. No one wanted to say it outright, but the thought was there, hovering in the background of every late-night analysis. What if we are being observed? What if this is not just debris but a fleet of relics drifting across the galaxy, each one a shard of some long-lost civilization? Skeptics pushed back hard. They reminded their colleagues that nature is stranger than we imagine, that the universe has always produced phenomena that defy explanation until better models emerge, that extraordinary claims require extraordinary evidence. To call Atlas artificial without proof would not be bold. It would be reckless. The history of astronomy is filled with such missteps, from Martian canals to misidentified pulsars. Better to assume nature until forced otherwise. And yet, even the skeptics admitted privately that the timing, the swarm, the glow, together they created a story difficult to dismiss entirely. For the public, the debate was less careful. Online forums filled with claims of alien probes, fleets, messages written in the green glow. Documentaries speculated openly about observational contact. Every image of Atlas was dissected, every detection of a swarm object treated as evidence. Scientists tried to temper the frenzy, but in doing so they only seemed evasive. The more cautious the experts sounded, the more certain the public became that something was being hidden. Watching the watchers turned into suspicion of what they were not saying. The idea of alien technology was irresistible, regardless of the data. And so the question lingered: alien tech or natural wonder? The data leaned toward the latter, but the unease leaned toward the former. The truth may never be known. Atlas will pass, the swarm will disperse, and the fragments will fade back into the dark. But the memory will remain, the suspicion that for a brief time the sky may have carried not just rocks and ice, but something more. Whether it was technology or geology, the lesson was the same. The galaxy is vast, its contents diverse, its visitors unpredictable. Each one carries messages written in chemistry, in orbit, in presence. Atlas carried more than most, enough to unsettle certainty. Natural wonder or alien artifact? Either answer is extraordinary. And the fact that we cannot yet tell the difference may be the most important message of all. There is a way the sky begins to feel different when coincidences stack too neatly, when separate anomalies all lean in the same direction, as if pulled toward a single point. With Atlas on approach, the swarm multiplying faster than catalogues could contain, and the strange chemistry of its green glow refusing to be dismissed, astronomers began to notice that everything was converging on a single span of time, September through December of 2025. That window became the focus of endless calculation, speculation, and anxiety. It was not prophecy, not an event pinned to certainty, but a recognition that patterns were clustering, the convergence window. At first, the term was only a shorthand in emails, a way for researchers to refer to the period when Atlas would make its closest pass through the inner solar system. But the phrase carried weight. It suggested more than orbital dynamics. It implied a moment when probabilities would peak, when trajectories would tighten, when all the uncertainties being tracked would reach their narrowest margins. For planetary defense, that meant it was the window when the risks would be clearest, whether for reassurance or alarm. For the public, once the term leaked, it sounded like destiny. The science behind it was straightforward. Atlas's orbit would bring it near Mars, then swing it sunward on a path that intersected Earth's orbital distance later in the year. Not a collision course, but a geometry that placed it within reach of resonance effects, gravitational nudges that could alter its trajectory, or that of any companions in the swarm. Many of the multiplying objects were on orbits timed to reach their closest approaches in the same span. Each was uncertain on its own, but together they pointed to late 2025 as the moment of greatest density. The dominoes were not falling randomly. They were all tipping toward the same season. For astronomers, this created a frenzy of observation. Every telescope capable of tracking faint moving objects was booked. Radar facilities prepared for their chance to bounce signals off the larger members of the swarm. Space-based observatories adjusted schedules to capture spectra and light curves. The idea was simple: collect as much data as possible during the convergence window, when the swarm would be brightest, fastest, and most numerous. It was an opportunity unlike any before. It was also a risk unlike any before. Models painted different pictures. Some showed the swarm dispersing harmlessly after its closest pass, fading back into the background population of near-Earth objects. Others showed fragments being pulled into resonant orbits, guaranteeing returns in decades or centuries. A smaller fraction showed direct impacts, probabilities still low but no longer dismissible. Each new calculation updated the odds, narrowing some, widening others. The result was not clarity but tension. Everyone knew that late 2025 would be decisive, not because it guaranteed disaster, but because it guaranteed answers. The public reacted in predictable waves. First curiosity, then fascination, then fear. The term convergence window appeared in headlines, stripped of nuance, presented as a countdown. Social media turned it into a clock. Memes showing calendars with September circled in red. Hashtags imagining what the last holidays of humanity might look like. Scientists tried to clarify, to emphasize uncertainty, but their words struggled against the gravity of the narrative. A window suggests an opening, and an opening implies something passing through. The imagination filled in the rest. Governments did their own calculations behind closed doors. Contingency plans were updated, emergency agencies briefed, military communication lines checked. No one admitted publicly that they were preparing for impact, but the signs leaked. Stockpiles of medical supplies grew. Naval exercises included scenarios of port evacuations. Satellites were repositioned for better tracking. To those paying attention, it was obvious that the convergence window was being treated as more than an academic curiosity. It was being treated as a moment of potential crisis. The psychology of windows is powerful. A diffuse threat stretched over decades is easy to ignore. A concentrated threat fixed to a few months commands attention. The swarm had been unsettling in its persistence, but the convergence window turned unease into urgency. Suddenly there was a date, a season, a point to watch. Even those who dismissed the risks found themselves counting down, aware that something unusual was coming whether or not it proved dangerous. Within the scientific community, debates sharpened. Some argued that the focus on late 2025 was exaggerated, that the swarm was no different from past waves of discoveries once biases in detection were accounted for. Others insisted that the clustering was real, that the convergence was not just perception, but mathematics. The argument became less about data and more about interpretation, about how much weight to give coincidence, how much trust to place in models built on incomplete information. The convergence window was as much a test of human psychology as of orbital mechanics. In quieter moments, some researchers admitted to feeling something deeper than analysis, an almost primal sense of being watched. The swarm seemed to respond to Atlas, appearing in patterns that defied expectation. The green glow of the interstellar visitor was brighter than models predicted, as if marking the season of its closest pass. It was easy to dismiss such feelings as projection, as the human tendency to find design where none exists. Yet the unease lingered. The convergence window felt less like a calculation and more like an appointment. That sense of appointment coloured everything. News specials counted down the weeks. Books appeared with titles hinting at doom or revelation. Religious voices interpreted the convergence as sign or prophecy. Financial markets, sensitive to uncertainty, reacted to every new discovery, every updated probability. A world already fragile under the weight of its own crises now carried an additional burden, the thought that the sky itself had set a date. And yet, for all the fear, there was also wonder. The convergence window offered a chance to see the solar system in motion as never before, to watch swarms of objects sweep past in real time, to gather data that would refine our understanding of both local and interstellar dynamics for decades to come. Even skeptics admitted it was a once-in-a-lifetime observational opportunity. Whatever else it was history in the making, written not in speculation, but in trajectories and light. The watchers prepared as best they could, their instruments pointed, their algorithms tuned. The public braced, caught between fascination and dread. And in the skies above, the swarm moved steadily, indifferent to human calendars. The convergence window was coming, not as fate, not as prophecy, but as geometry. The cosmos had aligned its motions to cross paths in a single season, and humanity could only watch, calculate, and wait to see what passed through. The closer the swarm drew, the harder it became to believe that what was unfolding in the sky was random. Astronomers insisted that chaos is not the same as disorder, that orbital mechanics can appear erratic while still obeying strict physical laws. Yet for those staring night after night at screens filled with new detections, faint moving dots multiplying across fields of stars, the impression was not of randomness but of arrangement. The swarm seemed to grow in layers, objects appearing in clusters that echoed one another, their paths crossing in ways that felt less like coincidence and more like choreography. It was easy to dismiss such impressions as the mind's hunger for patterns, but the hunger was fed by numbers that stubbornly refused to smooth into chance. probability models strained under the weight of new data. One or two outliers can be explained as noise. Dozens, then hundreds, create a different problem. The orbital inclinations of many swarm objects did not scatter evenly, but grouped around narrow bands. Their entry velocities, though varied, often hovered within similar ranges. Some appeared in bursts, as if arriving together rather than independently. In statistics, such clustering is expected occasionally, but the frequency here pressed against credibility. The numbers bent toward pattern, and the more they bent, the more the idea of chaos gave way to unease. The watchers were divided. Some clung to the comfort of chance, reminding colleagues that human eyes and minds are tuned to find order even where none exists. Constellations, after all, are nothing but random alignments of distant stars. But others admitted privately that what they were seeing did not feel like mere illusion. A sequence of arrivals timed so tightly with Atlas's approach, a multiplication so rapid in so short a span, it was hard to call that random. Patterns were emerging, whether imposed by human perception or by the physics of something deeper. The public, watching from the outside, had no such hesitation. To them, the swarm was already a pattern, a signal written in the heavens. News anchors spoke of hidden order. Commentators speculated about intent. Conspiracy theories flourished, suggesting orchestration, warning of fleets or probes disguised as natural bodies. Scientists tried to push back, offering explanations in terms of gravitational focusing, resonant capture, observational bias. But the harder they pushed, the less convincing they sounded. The narrative of pattern had momentum, and momentum is difficult to arrest once it begins. Yet the strange thing was that even the sober explanations hinted at structure. Gravitational focusing by Jupiter could indeed channel multiple objects along similar paths. Resonances could trap or release clusters together. The solar system's architecture itself can create the illusion of choreography, with objects funneled through the same corridors by forces invisible to casual eyes. If so, then the swarm was not random at all, but the product of cosmic design. Not deliberate, not intelligent, but pattern nonetheless. The chaos of interstellar debris was being shaped by the gravity of our system, sculpted into forms that looked ordered because, in a sense, they were. Still, the coincidences piled up. Certain objects passed close to Mars within days of each other. Others lined up in orbital elements as though belonging to families, despite supposedly arriving from different directions. A handful even seemed to echo Oumuamua's trajectory, as if fragments of some larger stream passing through over centuries. Each new detection was another thread, and together the threads began to weave into something that looked less like noise and more like tapestry. The watchers could not agree on what it meant, but they could not deny that it was there. In history, the search for patterns in the sky has always defined humanity. Ancient civilizations mapped constellations, tracking stars not just for navigation but for meaning. Eclipses were read as omens, comets as messengers. Science was born from that same impulse, the desire to extract order from the heavens. Now, centuries later, the swarm reopened that old reflex. Were these objects just rocks and ice, obeying blind physics, or were they participants in some larger geometry of the galaxy, a pattern too vast to perceive fully? The question lingered not only in the public imagination, but in the minds of the watchers themselves. Some speculated that the patterns might be the signature of the interstellar highway itself, debris streaming along invisible lanes shaped by galactic forces. If so, then the swarm was not coincidence, but evidence of structure on a scale humanity had never before recognized. Others whispered of darker interpretations, that the alignment was too clean, too coincidental, that perhaps intelligence lay behind it after all. No one dared publish such thoughts, but in late-night conversations the possibility was acknowledged. The line between chaos and order had blurred, and in that blur anything could be imagined. Psychologists warned that the human brain is incapable of tolerating true randomness. Given enough data, patterns will always be found, whether they exist or not. But the watchers countered that the patterns in the swarm were not subtle, not illusory, but quantifiable. Inclinations, velocities, clustering in time, all measurable, all undeniable. The debate was not about whether patterns existed, but about what caused them. Natural forces or something more. The convergence window gave the question sharper edges. If the patterns held, then late 2025 would see the densest clustering, the clearest expression of whatever forces were shaping the swarm. For some, that meant the chance to confirm natural explanations, to show how orbital mechanics produces apparent order from chaos. For others, it was a test of the darker hypothesis, the moment when the truth of orchestration, if it existed, might reveal itself. Either way, the patterns pointed forward, as though the chaos was funneling into a single decisive moment. The effect on society was predictable. Markets reacted to the idea of order in the swarm, interpreting it as sign of predictability even when none was promised. Religions framed the patterns as messages, divine or otherwise, connecting them to prophecy. Fiction writers and filmmakers rushed to imagine scenarios where the swarm was fleet, probe, or harbinger. The very word pattern carried weight. It reassured and unsettled at once, suggesting that the universe was not blind after all, but guided by some hand, natural or not. The watchers, for their part, did not agree. Some doubled down on skepticism, insisting that to see design was folly. Others leaned into wonder, admitting that even natural patterns are awe-inspiring, that to witness them is to glimpse the hidden structure of reality. What united them was exhaustion. The flood of data continued, detections piling up night after night, each one a reminder that the swarm was real, not rumour, and every time they looked for randomness they found patterns instead. In the end, the debate may never resolve. Whether the swarm is a coincidence of trajectories, the signature of galactic highways, or something more deliberate, the patterns are there. They speak not in words, but in alignments, in clusters, in echoes across space and time. The chaos of countless rocks and fragments drifting through the void has, for a brief moment, arranged itself into something humanity can recognize. And in that recognition lies both fear and fascination. The swarm does not explain itself. The patterns may dissolve as quickly as they appeared, fading back into the randomness of the sky. Or they may sharpen into revelation, pointing to truths humanity is not yet ready to face. For now, all that can be said is that in the chaos of Atlas's arrival, patterns emerged, and once seen, they cannot be unseen. When the story of Atlas and the swarm is told, the most important realization is not about a single comet or a fleeting window of danger. It is about perspective. For centuries, humanity has looked at the sky and thought of it as background, as stage, as something distant enough to admire without being threatened by it. The multiplying object shattered that illusion. The swarm forced the recognition that the galaxy is not far away. It is here, moving through us, weaving our system into its vast machinery. And if that is true, then humanity is not an isolated species huddled on a fragile world. It is, whether it is ready to admit it or not, a citizen of a larger galaxy. That phrase was not coined by poets or philosophers, but by scientists searching for language to capture what was happening. The interstellar highway, the patterns in the chaos, the convergence of trajectories, all of it pointed to a simple truth. Our solar system is not unique, not sealed off, not exempt. It is one node in a web that stretches across the Milky Way, and material from other places will always find its way here. Each fragment, each visitor, each comet glowing with alien chemistry is evidence of that citizenship. We do not choose it, we inherit it. To become citizens of a larger galaxy is to accept vulnerability. The swarm showed that in painful detail. Objects from beyond can threaten oceans, cities, entire continents. They can arrive with little warning, overwhelming our systems of vigilance, defying our capacity to respond. The illusion of safety built by centuries of distance collapsed in a matter of months. We live not in a quiet neighbourhood, but on the edge of highways carrying debris from countless worlds. That realisation is humbling, terrifying, and essential. But citizenship is not only vulnerability, it is also connection. Atlas carried with it messages in chemistry, fragments of a story written in elements and isotopes that spoke of other stars, other births, other deaths. To study it is to read across light years, to learn that the galaxy is not uniform but diverse, filled with environments that produce wonders we can barely imagine. Each visitor is not just a threat but a teacher, bringing knowledge no probe could otherwise deliver. Citizenship means participation in that exchange, willing or not. The galaxy shares its fragments with us, and through them we begin to understand our place. For the public, the lesson was uneven. Some embraced the idea with awe, imagining humanity as part of a cosmic community, a species living in a galaxy alive with traffic and exchange. Others recoiled, unnerved by the thought of forces so vast and indifferent that they make our civilizations look fragile and temporary. The swarm divided opinion but united attention. No one could ignore it. Everyone, from scientists to schoolchildren, found themselves looking upward, aware that something extraordinary was happening above. In that awareness lay the first step towards citizenship. Governments too absorbed the lesson. For decades, planetary defense had been treated as an afterthought, funded modestly, discussed occasionally, but never prioritized. The swarm changed that. When the multiplying detections threatened to overwhelm the watchers, when the convergence window loomed, when simulations of ocean impacts and city-killing airbursts filled reports, the reality sank in. To live in a galaxy alive with traffic is to live with risk. Citizenship requires responsibility, preparation, vigilance. The fragile patchwork of detection networks and mitigation plans had to be strengthened, because the next swarm will come, whether in decades or centuries. That is what it means to belong to a galaxy larger than our imagination. The cultural impact was harder to measure but no less real. Art, literature and film absorbed the imagery of Atlas, the green glow against the dark, the swarm multiplying like omens. Religions debated the meaning of interstellar visitors, whether they were tests, signs, or simply reminders of creation's vastness. Philosophers asked whether humanity's sense of identity could survive the realization that Earth is not isolated but permeable, part of a galactic exchange that has been happening unseen for billions of years. These were not temporary questions. They will shape the way future generations think about themselves, their planet, and their role in the cosmos. The final months of 2025 became more than an observational campaign. They became a mirror. Every detection forced reflection not only on the cosmos but on ourselves. The Watchers, exhausted and determined, represented humanity at its most honest. Fragile but curious, overwhelmed but persistent. The public, anxious yet fascinated, represented the tension between fear and wonder. Governments, cautious but engaged, represented the slow awakening of responsibility. Together they illustrated what it means to be citizens of something larger. Not mastery, not control, but recognition and adaptation. The swarm will pass. Atlas will fade back into the dark, its glow dimming as it moves beyond the reach of telescopes. The detections will decline, the sense of crisis will recede, and daily life will reclaim attention. But the memory will remain. For a brief time, the galaxy revealed itself not as background but as presence, not as infinite distance but as immediate neighbour. The illusion of isolation was broken, and though it may be forgotten in moments of calm, it cannot be erased. To be a citizen of a larger galaxy is to live with paradox. We are small, yet part of something vast. We are fragile, yet connected to forces older than our planet. We are vulnerable, yet capable of understanding, of building systems to watch, to prepare, to respond. Atlas did not arrive with intent, did not carry messages in words or signals, but its presence was a message nonetheless. The galaxy is alive with motion, and we are part of it. Whether future visitors bring only wonder or catastrophe, or something beyond our capacity to imagine, the truth remains. Earth is not alone. The swarm reminded us of that in the most immediate way possible. Citizenship cannot be refused, only recognized. The galaxy does not ask for our consent. It grants us participation simply by existing. The choice we have is how to respond, with denial and neglect, or with vigilance and humility. As the last fragments of the swarm are catalogued, as the watchers finally rest, the lesson lingers. We live in a galaxy that sends us reminders, sometimes glowing green, sometimes silent and dark. Each one is both threat and gift, warning and wonder. To live in such a place is daunting, but it is also extraordinary. For all its risks, citizenship in a larger galaxy is also membership in something unimaginably vast. A story written across billions of stars with Earth as one chapter among many. And as we look back on the season of Atlas, on the chaos that revealed its patterns, on the fear that sharpened into awareness, we begin to understand that this was not an ending but an introduction. The galaxy has always been here. The swarm only reminded us to look up, to see ourselves not as isolated but as connected. Citizens at last of a galaxy far larger than we ever allowed ourselves to believe.